Hello, Dr. Anna and Professor Vivian. This is our the fourth part of our video, and it's about pushover analysis, nonlinear static analysis, pushover analysis, and nonlinear time history analysis. And nonlinear time history analysis is it's all the same as linear dynamic time history analysis. All the procedure, everything is the same. The only difference between nonlinear time history analysis and linear time history analysis is the modeling. For linear time history analysis, the modeling is linear modeling. We perform our analysis in linear modeling. But for nonlinear time history analysis and pushover analysis, we are going to use nonlinear modeling. So as we discussed, classical model analysis was performed on both 44 and 100 story building in the first part of the video, and in the second video also response spectrum analysis was performed, and in the third video also linear time history analysis was performed, and the results and everything was discussed. And for our research also we will use we can have a lot of papers from here comparing different parts and doing this. And now we are in the final part, that means nonlinear dynamic analysis. So as usual, first we have to change our model from linear to nonlinear. So for to do that, I use plastic hinge modeling approach for column and beam, and fiber hinge fiber modeling approach for shear wall. So I will show you, and let me go to ETABS. This is our model. We perform linear analysis, classical model analysis, response spectrum analysis, and time history analysis was performed for linear case. But now I have changed this model into nonlinear. So if I want to show you, if we go here in the nonlinear hinges, if I say apply, sorry, as you can see, this is the hinges. So the detailed explanation of what is plastic hinge modeling and fiber hinge modeling, if we go in that, it will take much time, but I will try to explain in the our presentation. I will try to explain what is plastic hinge modeling and what guidelines we have, and what is force deformation, what kind of hysteresis loop I assign for each for concrete and steel, and everything. I will try to explain it later, just for your information. Now as you can see, our linear model is changed into non-linear modeling now. So we are going to perform our pushover analysis and nonlinear time history analysis in this nonlinear modeling. Now we can capture the ductility of each member, the ductility levels and everything we can capture, because now we give all force deformation curves and the rules also, hysteresis loops, everything is assigned. How we assign it and everything I will come, but just for again, before I go, let me show you here. For example, define here frame. If I say show hinge details and show generated hinges, it will generate it will show us the whole hinges. It will show us the whole hinges. Okay, here as you can see, this is our beam hinge, moment M3 type hinge. We assign for all beams, both ends, and this is for our column. PM to M3 hinges are assigned for our columns, and the PM3 fiber hinge is assigned for our shear wall. So if you want to see, for example, moment here, modify and show, this is the force deformation curve we assign for each joint. As you can see, this is the force deformation curve we assign for concrete, and as you can see, this is moment rotation. This is the moment rotation, and this backbone, this is the backbone. As you can see, these are the points A, B, C, D, these are the points. This is where the ductility starts. This is where our material starts. This is A. Okay, this is point B, point C, point D, point E. Each point has its own explanation. I will come in the moment. This is hysteresis curve for this force deformation curve, the rule how it will degrade. So all important, this immediate occupancy, life safety, collapse prevention, everything is assigned. How we assign it, I will show you in a moment again. If you want to change the hysteresis type, you can directly go, you can change this into convert to user defined, and we can convert. So the same is true for our column also. For our column also, the same is true. Moment rotation, everything is given. The safety factors, load carrying capacity beyond P means after the curve drop to 0, because once the ductility is finished and the force deformation curve is finished, whether at point E it will drop or we extrapolate, but we make it drop to 0. No need to continue, because if you make it drop 0, once our structure ductility as per our assigned hinge, once the ductility, the material ductile and go to plastic range, then the program will terminate. So in this way, we just we can, so this is shortly how we make our structure from linear to nonlinear. It is very easy. Just we just select our beam, then we go here assign, then we just go frame, then hinges. Then now, because it is round, it is closed, but in this way we can make our structure nonlinear. So let's go to, this is now pushover analysis and nonlinear time history analysis will be performed in this model. So let's go here. This is plastic hinge modeling, this pushover analysis. So as I told you, this is force deformation curve A, B, C, D. What I showed you now is this is a point from A to B. This is the first part in the force deformation curve. When it passed to B, now this is the first point of the material ductility starts. Then we have IO, LA, CP levels. These IO, LA, CP levels, there are different guidelines. I will come in a minute. I will show you then when it reach C, then D, then E. So when it reach E, already the material is the capacity is already completed. So as I showed you in the now, if you make it drop to 0, this is the place where it will end, but if you extrapolate, it will continue. So in this introduction, what is pushover and everything, let me go and I will show you the result also, what kind of result we get from here, global responses and pushover curves, and we can find the result of each hinge as well, and ASC 4117 also, table 10.7 and 10.8 I will show you, because we have manual and automatic options. So let me open in this background, let me open our presentation slide. Let me open our presentation slide. We will come back to this and I will show you all the results and whatever we extract from this pushover analysis and what is the procedure and everything will come just in a minute. This is our presentation slide. Okay, this is pushover analysis. We have another slide. Okay. So just to remind you, the comparative analysis and design of 44 and 100 story multi-purpose high-rising RC building using performance-based design procedure and Ethiopian prescribed adopted RC building design course. That's what we use. Basically we just use response spectrum of Ethiopia. The other thing is all the same. So these are our buildings, 100 story and 44 story. The first three analysis was performed in linear, but now we changed it into non-linear, as I showed you here. We use plastic hinge modeling approach and fiber hinge approach for shear wall, as you can see. So our model is now non-linear, so we are ready to perform pushover analysis and non-linear times 3 analysis. So as per our discussion, linear static procedure, we have a linear static procedure and a non-linear static procedure. This is the non-linear static procedure, pushover analysis. Non-linear dynamic procedure, this is also non-linear response history analysis. Now we are going to see these two: linear dynamic procedure, response spectrum analysis, linear response history analysis, direct integration, and linear modal response history analysis was performed in last video. You can refer that. Now non-linear pushover analysis, capacity spectrum analysis, and displacement coefficient method, and various other pushover analysis, multi-mode pushover analysis we have also. Now we will discuss today. Just to remind you what is a gap. From extensive literature review above, from our extensive literature review, one can observe that there were huge amount of work was done on the comparison of the design of structure in different country cores, and performance-based design methodology was applied in different buildings. A lot of SAI or Indian code, different works, comparison works, design works was done within different code, adopted code and performance was. But to our knowledge, none of them did intensive and comprehensive RC design on 44 and 100 story buildings, and included almost all type of design procedures such as classical model analysis, response spectrum analysis, linear times 3 analysis in linear model, and as I showed you now, SPO, static pushover analysis, and nonlinear time history analysis on nonlinear modeling. So we have linear and nonlinear, and all will be performed in 44 and 100 story buildings with plastic Hinge modeling approach in one paper, and in the desired location of Ethiopia also. This research work become novel already, because the building type is 44 and 100, the structure is different, the location is different, the analysis also, almost all analysis is included, but specifically deliberately I didn't include this ELF procedure is not included, just deliberately, because ELF is mostly used for low rise buildings, so that's why we didn't do. And most guidelines also propose 7 earthquake data, but for this research I use 11 earthquake data extracted per website and are unique for this paper. This makes this paper novel and original and open door for future research works, because after we finish, now once we have linear and nonlinear models, we can play, we can change the response spectrum, we can change the material property, especially with Dr. Anna while studying for concrete. For example, if you have any type of including with greenhouse effect for different kind of concrete research, if we find different kind of as per your research, if we find different kind of concrete materials we can use for the design, we simply change the material property here. Let me open it. When the model is nonlinear, it's already very heavy, that's why it's the computer is very slow. So here, material property, when we define the material property in the concrete section here, now we can play here as per any type of research. If the material type, weight per unit volume, mass per unit volume, anything we can change here, so we can make the research different for different time. So as per different approach we can make this work novel. So as per, this is a gap, so response spectrum, everything was completed. So let me go directly to today's session. Just what I want to show you, I know you know it, but just to remind you what I am going to do. So we have the structural model, we have linear model, non-linear model. As I showed you, our model is already non-linear. I use plastic Hinge modeling. So static analysis, we have this equivalent lateral force procedure, response spectrum analysis procedure, modal response time history is completed, linear response history analysis procedure, direct integration. This is, we discussed in our last video the difference between this and this direct integration. We use numerical step-by-step numerical integration method, Newmark methods, and other methods like Ramdi-Kuta and other, directly without decoupling the equation of ground motion, the equation of motion. We can directly solve for D displacement, but here we use this orthogonality property and we decouple the equation of motion and we just solve for each mode. That's what we did. So when we come to nonlinear, several pushover analysis methods are there. Today we are going to concentrate here this one and this one, both. So we have pushover analysis, single mode pushover analysis, or we have other types. We will see nonlinear static procedures. We have a lot of pushover analysis types, single mode or multiple mode pushover analysis. We will see. So nonlinear model response history analysis is the same, fast nonlinear analysis using the concept of modal shapes. Here the only difference between time history analysis, modal response history analysis, linear and nonlinear, the only difference is the model type. All the procedure, the same ground motion, we are going to use the same thing, and only the analysis procedure we will have small few differences I will show you when it comes here. So pushover analysis, nonlinear time history analysis, today I will try to finish. So let's go to today. I think here time history analysis procedure, last time completed. Today the fourth video series on pushover analysis. Okay, this one, let's start now. Very quickly I will try to show, I know you know it, but for the sake of what I am doing, to show you what we are doing, let me explain it. Introduction to nonlinear static pushover analysis procedure. Introduction to nonlinear static pushover analysis. We have the capacity spectrum method, ATC 40, FEMA 356, the displacement coefficient method, ATC 40, FEMA 356. We have all these guidelines, and this was in 1996. This recommendation by ATC 40 was in 1996. Then we have also the updated one, the improved one, FEMA 440, improved nonlinear static pushover analysis, FEMA 440. This was AC 41, 06, 13. We have 17 also, but this one is in 2005. This one was improved, the improved version of it has the improved version. The same is true. So using these procedures, capacity spectrum method and displacement coefficient method, this both I will show you in a minute also. We will use these two methods for estimating our target capacity, target displacement, because we are going to push our structure until this target displacement, and we are going to extract the demand, how our building, the capacity of our building until that displacement in the future earthquake. When the future earthquake comes, the building will be pushed to this amount of target displacement, or we call it performance point. Once we know these performance points, then we are going to assign, as per our nonlinear model, we will assign our force deformation curves and the hysteresis rules together for that capacity. That is the idea of performance based. But to know what is the target displacement, that is the problem. So we will come, and how we are going to find this target displacement we will discuss. So approximate method, multi-mode based seismic analysis procedure. This is multi-mode based. This one is for single, okay, single mode, because when we apply pushover analysis, the first one is single mode only. For example, the first mode forces will be applied, and it will be step by step for different steps from lower to higher. The building will be pushed, and for each step we will extract the displacement and base shear, and we will construct the pushover curve. So in that way I will come. But for multi-mode based seismic analysis procedure, we have the modal pushover analysis procedure, and we have the uncoupled mode response history analysis, UMRH procedure. We have these two methods, and we will discuss. And just for the acknowledgement, I am using most of the slides of Professor Dr. Fuad Najim. He is a great man in the earthquake structure. I recommend to check his videos and books also. So just I acknowledged from where I took. Okay, an introduction to the nonlinear static pushover analysis procedure. So as I showed you, we have linear and nonlinear procedure. So we are here now. So nonlinear static analysis procedure, pushover analysis procedure. The nonlinear analysis recommended for the first generation of performance-based seismic design methodology. Currently, it can be regarded as an alternate method of analysis for carrying out the PBD. Instead of carrying full nonlinear dynamic analysis, we can use pushover analysis. For example, we have nonlinear model here. instead of carrying a full nonlinear dynamic analysis, we can use pushover analysis. What we are going to do, we have already nonlinear model here, so we have control node here. So what we are going to do, this is monotonic pushover analysis. That means we have only one mode. For example, this is the force, for example the first mode force. So we are applying it progressively, starting from lower to higher. Then each progress monotonically increasing lateral load pattern from F1 to Fn. Then the pushover to push the structure in that particular X or Y direction. So here, once we push it, then we are going to extract for each push, starting from 0, the displacement here, XR, the displacement in the base shear will be taken for the first push here. What is XR and the base shear here? Base shear means just the cumulative of forces, each forces in our structure. Then when you add up, the summation will become base shear. So this is how we are going to construct pushover curve. This is a relation between base shear and displacement. So this is a basic concept of pushover analysis. So monotonic pushover analysis means only monotonically, but we can make it also, instead of monotonic pushover, we have also multi-mode. I will show you. So as you can see, a ground motion in the particular X or Y direction, we have XY direction, and we have full 3D nonlinear multiple degree of freedom mode. We can make that. Okay, we can make that. For example, let's set the control node as a roof node here, and denote the peak inelastic roof displacement occurred during the ground motion as X inelastic R. So X inelastic R, when we have ground motion here, then the maximum X inelastic because of this ground motion, let's call it X inelastic, and perform full dynamic analysis and extract the responses and find the displacement, and finding velocity and acceleration will be easy. But instead of doing that, this is equivalent to, we have monolithic, as I discussed, we have control here, we push it progressively, we construct the pushover curve, then structural demands at this point, seismic demand. For example, for our any other building, if we know this point XR in elastic, if you know XR in elastic, then directly take this point and we can get our base shear, and we can design our building from pushover analysis for here. This, if we know the maximum target displacement. So during the push, when XR is equal to X in elastic, the force and displacement demand of the structure are the peak seismic demand produced by the ground motion. So once we construct this, we will know the X in elastic, the target displacement we will know, and we know the future earthquake also. For that earthquake, this is how much the building will be pushed, and for that amount of target displacement we can extract all moment, shears, displacement, drifts, everything about our building, global or local response of our building can be extracted, because we know the base shear, and through the base shear, once we know that, we can design everything. The most important question is how to determine XR in elastic for our building, and what load pattern to apply. This is a two question, very important question. What kind of load pattern we have to use for pushover analysis, and what is the maximum X in elastic, the maximum target displacement for our building. These are the two questions. If we know these two, if we know the pattern of what kind of pattern of load we have to use and the target displacement, then it will be easy to calculate. So lateral load pattern in pushover analysis, there is a lot of researchers, they use what kind of load pattern we have to use. For example, start with gravity load. This is normal, dead load, seismic portion of live load. Then static lateral load pattern. For example, uniform rectangular load like this. Distribution of pushover force. And the force is equal to phi. This is the mode shape times W, the weight of each floor. Then it will give you force. And once we know the force for each floor, then summation of Pi will give you total force. That means base shear. So this is one part. Code specified static lateral load distribution. Also there is different codes, different guidelines. Inverted triangle also, as I showed you here in the first, inverted triangle. This one, inverted triangle. Again, first mode shape. This is mostly we use the first mode shape. Once we complete the modal analysis, classical modal analysis, then we can use the first mode shape from there. So we can assume that the building will primarily deform in the first mode shape only. There is no other contribution from higher mode, second mode, third mode, fourth mode. We simply assume that the first mode is dominant. So it is also called modal inertial mode pattern. This is the first mode forces. We call the modal inertial mode pattern also. Then combination of mode shape. Again, there is in the multi-mode shape pushover analysis, we will see that different modes, first mode, second mode, third mode, fourth mode, then each mode will be applied, and the response from first mode, second mode, third mode, fourth mode, and the higher modes will be SRSS them to find the final response of a structure. Lateral load pattern in the pushover analysis, we saw it already. Generally, the deformation pattern corresponding to the first mode inertial load pattern. This is the first mode inertial load pattern is used to the basis of analysis. As you know, we have M times mode shape phi y mode shape times mi. That means for that level. So where Fi is lateral force at any i's story. Okay, mi is the mass of any i's story. Phi I is the first mode shape vector for that story again. So when we multiply this, we will find force. When we sum the force, we will find base shear. This is generally acceptable for a structure with time period less than or equal to 1 second. For more flexible structure, the contribution of higher vibration modes may become significant and need to be considered in the pushover analysis. So this, as I told you, we will see in the second part. Multi-mode pushover analysis will be also discussed. Pushover analysis for performance evaluation of a building. Okay, this is horizontal load pattern. Just to summarize, we have vertical load here and we have horizontal. So pushover analysis will be performed here. Then as per pushover analysis, that means progressively we will apply these loads F1, F2, F3 for different steps, and we will construct our displacement with base shear curve. This is pushover curve. And if we know X in elastic, this is sometimes we call it performance point or target displacement, and we will take this point and this will be our performance. Then we will take base shear at this point and we will design our building at this point. So pushover analysis procedure: construct the nonlinear structural model. This is the nonlinear structural model. Apply gravity loads, apply horizontal load pattern using first mode shape. This is the first mode shape, and incrementally apply the pattern to get the pushover curve. So this one will be applied incrementally, not one time, incrementally, and we will construct the curve. Then determine the performance point. This needs a separate method to estimate. We have to estimate, because to know this one we will discuss later. Evaluate the structure performance at X in elastic R, pass or fail criteria evaluation on the component by component or global structural basis. Once we know our performance, then we will use this point as a performance point. We will apply this point as a performance point. So when we apply our force deformation curve, plastic hinge modeling, when we change our model from plastic to inelastic, from elastic to inelastic, so this one is now nonlinear model. This is our nonlinear model. So when we assign these hinges are performance point. That means we will assign force deformation curve, okay, moment, rotation, or any. For this particular, we use NLTHA curve for each hinge, and hysteresis rule as well. So as per our for example, as per our force deformation curve, the performance or the capacity of our building will be assigned. In the future earthquake and any force, when it comes above that performance point, then our nonlinear model will capture. It will show us that now it is past our limit, and it will go to plastic state. So that is how we are going to do. So performance point, a point on the pushover curve corresponding to the likely peak inelastic control node, displacement x inelastic during the ground shaking. In other words, the future earthquake is expected to push the building to this point only. So once we know the ground motion and once we know our target displacement, so the ground motion which will come, okay, the earthquake or whatever will come and push our building until that target displacement. Then as per that target displacement we can design. XR inelastic is also sometimes referred to as the target displacement. So as per that, we have global response and performance. This is structural displacement in this load. So sometimes we can, this is they call it X-ray of our building, because as per the target displacement, once you know your displacement, you can know where is your building. It will be in the immediate occupancy level, or it is in the life safety level, or in the collapse prevention level, or already it is collapsed at E point, as I showed you. So once you know your target displacement, you can know which level or operational level. As I showed you, this is the first part, A, B, C, like that. You can add also. So this part all is immediate occupancy level, and all levels have their own definition. So this is also Professor Fawad. They did some experiment in Perform 3D, because this one is captured in Perform 3D. We cannot capture this in ETAPS. This is pushover curve of an example 44-story RC shear wall building, a strong X direction. So as you can see, roof displacement, top displacement of the building in this direction. Okay, this one is top displacement divided by building height. This is normalized by height. And this one is base shear divided by building weight also. So as you can see, when the curve is going, at this point brick wall begin to crack, at this point shear wall begin to crack, again at this point shear wall steel reinforcement begin to yield, at this point column begin to crack, at this point shear wall steel bar begin to yield. Again, when it reach at this point, concrete crushing in shear wall. Like this, here column steel bar begin to yield. Again here column bars begin to yield in the compression. So in each step of the push, what kind of which element of your building has effect, you can capture that. You can capture that. That is the beauty of nonlinear analysis, performance-based analysis. It will give us component level, element level performance, not as a whole, but we can see like this. It will give you the progression as well. So this one, monotonic pushover analysis result. This is as we have discussed, this is the roof drift, this one is shear wall, this one is normalized base shear. So base shear with roof drift is constructed, but in this time in the positive and negative direction was performed. This is 20-story building. First mode in the y direction was applied. Apply push and pull forces in the same analysis and pick the peak deformation for each cycle. For each cycle you will find the base shear and roof displacement. So base shear, roof displacement, and you construct the pushover curve in this way, and in the negative and the positive, because it will go in both directions. This is how the pushover curve is generated. Again, this one, the reverse cyclic. Instead of only monolithic, you can make cyclic also. Okay, you see, this is cyclic pushover. This is monotonic pushover in positive direction and monotonic pushover in the negative direction. So we have cyclic and we have monotonic pushover also. So how this one, let me show you. I have one video also. This is the same building from Professor Voigt. Let's open this one. How this is base shear, roof displacement. Let's play it. So when you apply the force, you see the progressively they apply the force. I think this they capture it by perform 3D, and the roof displacement in the base shear, the hysteresis will be it will capture the hysteresis for you. So this is 40 seconds. Yes, okay, just for your information. So this is how this cyclic pushover, the cyclic pushover, both side cyclically, and they will capture the hysteresis loop here. So as you can see, also the same column begin crack. This one, this will capture in the perform 3D, I think. So the same things I did. This is mode 1 in different buildings, 20 story, 30 story, 44 story, and this is also the same mode 2, and this is mode 3. So when they apply first mode shape and push the building, they will get this kind of hysteresis loops. For 33 buildings, this for 44 buildings, they will get this. So it is normalized, like they just divided with h, and this one is divided by the weight of the structure. Again, for the second mode is like this, the third mode is like this. Is analytically we can find the hysteresis loop, and we can use this backbone just to find our the capacity as well. But this one is some. So once we know how to do it, so the concept of equivalent single degree of freedom system, this is very important. We have to know. Let me show you. So as we discussed, we have full 3D nonlinear multiple degree of freedom system we have here. So what we say is, instead of performing full dynamic analysis, we can apply force and capture the target, the performance point for each step, and construct your pushover curve, XR over base shear, displacement base shear. Then this is the point. We can use idealization of pushover curve. you can idealize this pushover curve with the bilinear or trilinear curve 1, 2, 3. Then after we change base shear to displacement into force deformation curve. Once we know the pushover curve, and by application of this force, and we find this pushover curve, we will change it into idealization of pushover curve, force deformation curves. Then we will assign this force deformation curve to our single degree of freedom system. So an equivalent single degree of freedom system will be assigned this. We have mass and we have k. K will be assigned this force deformation curve. Not only force deformation curve, I will show you later also, we will assign hysteresis rule also. How will loading and unloading will apply. Then this single degree of freedom system now start behaving like multiple degree of freedom system, because once we get any response from here, we can change it into multiple degree of freedom system. So converting a nonlinear multiple degree of freedom system into an equivalent nonlinear single degree of freedom system, this is very important point. How to get the target displacement of performance point. First, perform monolithic pushover analysis. I showed you here now. Monolithic, this one is monolithic because in one side. But we can make also cyclic also. Procedure on nonlinear model. And generate pushover curve. Base shear versus deformation curve. Base shear versus deformation curve, and we will change it. Second, convert the pushover curve to idealized force deformation curve like this, and use it to model an equivalent nonlinear single degree of freedom system. This is very important concept. This is how pushover and other concepts comes. So this is the main idea, how to convert this and comes doing this. Cyclic pushover, as I showed you now, we have cyclic pushover also. You have base shear and roof displacement, and we will normalize it with dividing with weight, and this one is dividing with height. How to change it here? Normalize base shear. We have base shear here divided with W, and we will change it to force. Again, roof displacement XR HR, change it into displacement. Then once we find this, then we will assign it to single degree of freedom system. So we apply also damping. Then this this nonlinear single degree of freedom system now represent the actual nonlinear multiple degree of freedom system. So as I showed you now a while ago, this is how we do. Once we capture this hysteresis loop, then we can use it. Okay, this is assumed converting a nonlinear multiple degree of system to a single equivalent nonlinear single degree of freedom system. In addition to the force deformation curve, we should give hysteresis rule as well. This is the hysteresis rule. When loading unloading curve. So how, when the loading and unloading is there, degradation, we have to the force dissipation methods, as you can see here. When the first one is KD, so when you go down, it will be multiplied with R. What is R? dy over dm here. So there is a rules. We have to assign this hysteresis rule to our force deformation curve, and we will give it to as stiffness, and assume damping, then we can find. Okay. So in addition to force deformation curve, we have to give the hysteresis rule as well for loading and unloading rule to our nonlinear single degree of freedom system as a stiffness. Okay. How to determine performance point or target displacement? As I showed you, what kind of load pattern and what kind of performance point and target displacement. How to get because once we know that target displacement, then we know the capacity of our building. So I am showing you this, just I know you know it, but just to demonstrate what we are doing in our research, because this is the basic concepts. So just I want to show you that the basic concept what I am using. So so we have performance point for target displacement on pushover curve. Once we have pushover curve, how to find performance point? There is a lot of methods. The first one is equivalent linearization approach. We already see how we change multiple degree of freedom system into single degree of freedom system. Equivalent linearization approach is the first approach. So in this approach, we have several equivalent linearization procedure, individual studies. There are a lot of individual studies. We have capacity spectrum method, ATC 40, FEMA 273, and FEMA 356 in 1996. And this is FEMA 440 improved version also. We have equivalent linearization approach we have. So it was improved from 1996, then this is to 2005 also, FEMA 440. So what is equivalent linearization approach? The idea is that we can convert our equivalent non-linear single degree of freedom system. We have non-linear single degree of freedom system, which is basically representing our actual non-linear multiple degree of freedom system as we have seen now. Through pushover curve, we can convert that equivalent non-linear single degree of system to linear single degree of freedom system, and we can easily estimate the peak displacement. That is the idea. Okay, that is the idea. Once we have the non-linear single degree of freedom system, once the procedure as we have seen here, once we assign all hysteresis, force deformation curve, everything, then again we have to change that non-linear single degree of freedom system to linear single degree of freedom. That is the idea, but we will see in detail capacity spectrum method shortly. Displacement modification approach. This is the second type. This is the second method. Several displacement modification procedures are there, individual studies. Displacement coefficient method, ATC 40, FEMA 273, and FEMA 356 are there also. FEMA 440 improved, just like capacity spectrum method. FEMA 440 improved one in 2005 was published, and we will see that. So we will see that our concentration will be mostly capacity spectrum method and displacement coefficient method for our prediction of target displacement or performance point. That's what we are going to do. So this is the building. This is our multiple degree of freedom system. We changed it into single degree of equivalent single non-linear single degree of freedom system. Then we perform this one pushover analysis, and we have the curve. We estimate the target displacement, then we generate the pushover curve, then we idealized it, then we assign that idealized force deformation curve into our non-linear single degree of freedom. Then we will change this to single degree of freedom system, linear single degree of freedom system, and we apply the ground motion and find the displacement, and we will use it for multiple degree of freedom system. That is the idea. Displacement modification approach, it is simply says that we can apply different displacement modification coefficient or factor to a displacement of elastic single degree of freedom system. So once we convert from non-linear degree of freedom system to linear degree of freedom system, then once we find the displacement, we will apply different coefficient. I will show you in a minute. C1, C2, C3, C4 for as per ASC 41. Then by applying these coefficients, we can get the target displacement. The last one, nonlinear response history analysis of the equivalent single degree of freedom system. This is the third option. This is the third option. What it says, the third approach is we simply perform the dynamic analysis on equivalent nonlinear single degree of freedom system. Simply we will apply the load. We just shake it under the future earthquake and calculate its peak displacement and convert that peak roof displacement of multiple degree of freedom system, then we are done with the Pushover analysis. So this one is very easy. Once you have your nonlinear degree of equivalent nonlinear degree of freedom system, we can directly apply the force and we can convert it into multiple degree of freedom system. But we have to make this for each nonlinear degree of freedom system. We will discuss in the coming slides. Originally, capacity spectrum method and displacement coefficient methods were proposed by ATC 40 in 1996 for the performance assessment of buildings structure, but in 2005 FEMA 440 improved both of these procedures to develop the improved capacity spectrum method and the displacement coefficient method. So on AC 4113 onward, we have thus improved methods as a primary nonlinear procedure method. This is just for information. So let's continue now. Equivalent linearization approach. The capacity spectrum method is as per our equivalent linearization approach. So we have capacity spectrum method as per guideline of ATC 40 in 1996 and FEMA 273, FEMA 356. So what it says, capacity spectrum method, FEMA 440, convert the pushover curve to spectrum acceleration and spectrum displacement. This is capacity spectrum. Again, response spectrum. The response spectrum is response spectrum with time converted into acceleration to displacement response spectrum. ADRS, acceleration displacement response spectrum. This is the demand curve. Then we overlaid, and the common point, the intersection, will be the performance point. We will see, but this is not easy. I will show you now what does it mean. So analysis procedure in ATC 40 for this method. How to change the curves, how to change, as I showed you, convert pushover curve to spectral acceleration and spectral displacement, and the response spectrum convert to acceleration to displacement response spectrum, and lay one graph to another graph, then find the performance point. So we shall see. Analysis procedure in ATC 40. Analytical procedures, as we discussed, this is a capacity. So we have force displacement. We perform, let me make it a little bit. So we perform pushover analysis, and we will find pushover curve, and we will change it into force to displacement. So the for displacement curve, we have it, then we will assign. So using this curve for the demand part, the capacity spectrum and the displacement coefficient method, both they use this curve. So demand spectrum, as you can see, we have the demand. This is the demand spectrum, and we have the capacity also. We have the capacity. Then when we have to reduce it also. This one, as you can see, the demand, we reduce it. So we will see how we have to reduce it, how we will reduce it, and we will put the capacity overlay, and the intersection will be the performance point. Once we know the performance point, we go in our load capacity, then we will check the performance using the performance point or target displacement, the global response of the spectrum, table 11.2 I will show you, and individual component deformation. Then we will perform a specified performance of the building. We will perform the performance of the building. So let's continue. Conversion of a non-linear single degree of freedom system into an equivalent linear single degree of freedom system. Okay, let's say something about this one also. How we are, the basic idea of equivalent linearization approach. Once we have force deformation, this is the energy dissipated by hysteretic damping. So this is the energy dissipation. Then when we come to here, total energy dissipation by the equivalent viscous damping. So this is how the nonlinear single degree of freedom system with initial circular natural frequency and with initial inherent viscous damping. But here the damping will be added because when we change it from nonlinear to linear, because we are changing it into linear system, an equivalent linear system with elongated period and additional damping. So I recommend you to read, but the main idea is once we convert it from here to here, then once we know the displacement, as you can see here, we go to our spectral displacement. Okay, we have the time, spectral acceleration to this is our response spectrum. Once we know the time, then we go here and we can get the spectral displacement directly. The only thing we need is the time. Okay, once we have the period, the equivalent linear property, so we have our response spectrum. Once we know the time, okay, the period, then we go here and we can find the spectral displacement and we can integrate it. We can find derivative, we can find the velocity, and once derivative, we can find the acceleration. So the only thing we need is the time period, 2 pi over omega cube. So this is how we do, because this is MW equivalent. So once we know that, it's very easy to change. Okay, capacity spectrum method, ATC40. This one we already discussed. So we make monolithic pushover curve, then we have conversion of pushover curve to acceleration displacement response spectrum form. So as you can see, this is VP Becher over XR displacement. So we change it into a spectral acceleration to spectral displacement curve. This is a conversion. A spectral acceleration means this one, VB over W over CM. A spectral displacement means XR over R mass participation factor phi modal shape R. So spectral displacement is also this one. We know this from classical model analysis. T square over 4 pi square ST. We can use this or this. Then point by point we will change pushover curve to spectral acceleration to spectral displacement. This is the first part. Then determination of performance points. Once we change the capacity spectrum, this is a conversion of pushover curve to the capacity spectrum, and we have the demand curve also. This is demand spectrum modified for equivalent damping. So a spectral once we have a spectral acceleration for the demand part, a spectral acceleration with time. We have a spectral acceleration with time. So we have to change this spectral with time response spectrum into a spectral acceleration to spectral displacement. So we have the same format, spectral acceleration to spectral displacement. Then we will change spectrum acceleration for that building. We have response spectrum. So spectral acceleration to time, we have to change it into a spectral acceleration to a spectral displacement. Then once we change it, then we will overlay this curve with the spectral acceleration to spectral displacement, though this point will be the performance point. So the demand spectrum is the reduced form of 5% damping spectrum. So our demand spectrum, once we change it into spectrum acceleration to spectral displacement, then we have to reduce it. We will discuss that later. Once we find this performance point, then the determination response, okay, we will come here. So the extract the responses from the pushover database for this point. Once we know this point, we will come to our curve and we will find the Becher. Once we know the Becher, then we know for our building. Okay, so capacity spectrum, spectral acceleration to spectral displacement, the pushover curve. Then demand spectrum, because the demand we put our limit. Okay, spectral, another form of response spectrum. So reduced based on effective damping. We will see what is effective damping. Okay, original inherent damping plus additional hysteretic damping. So one more important idea is that the demand spectrum is not simply converting spectral acceleration to time into spectral acceleration and spectral displacement. It is a reduced form of that, because when you convert a nonlinear system into equivalent linear system, you are not only elongating its time period, but you also give an additional damping, and that additional damping will basically resulting in the reduction of your applied seismic hazard. So based on the effective damping, we reduce the acceleration displacement response spectrum, and that reduced spectrum should be plotted in a capacity spectrum to find performance point, this one. So we have here the capacity spectrum and we have the demand spectrum. So we will see. So capacity spectrum conversion, how we for the capacity, as we discussed, we have base shear and displacement. We will change it into spectral acceleration and spectral displacement. We have a lot of codes. We can see here capacity spectrum conversion. So this is SA, this is for spectral displacement, this is for spectrum acceleration, point by point how to change it, VI over W over alpha I. What is alpha here? Everything is given. Modal mass coefficient for the first natural mode. What is phi? Phi is here. Amplitude of mode 1 at level 1. So mode shape. What is PE1? Mode participation factor for the first natural mode. So all these things was discussed. Spectral acceleration, spectral displacement, everything was discussed in the classical model analysis. And what is mode shape, mode participation factors, everything you can use and you can change simply. This is a formula for PF1 alpha 1. So directly you can use and you can change. We can change. Then conversion of ADR spectra. This is a spectral acceleration to time. Then we have to convert it into a spectral acceleration to a spectral displacement. This is the ADR A conversion, acceleration displacement response spectrum. So you can read it, but this is a formula, a spectral displacement. This is a formula we have, and spectral acceleration and spectral displacement, how to change it. This is also the formula. Everything is given, only a matter of reading. But now let's go here. Reduction, how to reduce now. Reduction of response spectrum to get the displacement, the demand spectrum. Determination of hysteretic damping using equal energy dissipation rule. This is what we have to use, equal energy dissipation rule. So what it says, equal energy assumption. What it says, energy dissipated by hysteretic damping in one force deformation loop, of an actual nonlinear system is equal to energy dissipated by an equivalent amount of viscous damping in one harmonic cycle of an equivalent linear system. So this is what they use. So as you can see here, energy dissipated by hysteretic damping here, again energy dissipated by equivalent viscous damping is here in the other side. So when we equate these two equal, we will find this one. So this is equivalent dissipation by equivalent viscous damping, E equivalent, and this one is for nonlinear. Then when they equate it, this is the equation they found. 1 times ED di over 4 pi ESO. This is ESO, this is ED. So energy dissipated by nonlinear, this is energy dissipated by linear viscous damping. So when you divide these two, you will find the xi. For detail, see section 3.9 Dynamics of Structures by A.K. Chopra 2012, 4th edition. This is taken from Chopra book. So if you have interest on exactly how to come up this equation, you can refer there. Now, reduction of demand spectra. Okay, so EO here, okay, let me, okay, so EO means energy dissipated by damping, area of enclosed by hysteretic loop, area of parallelogram, ESO, okay, I think this one is ED, okay, this is ED, the area of parallelogram, this is ED. ESO, maximum strain energy, area of hashed triangle, this is ESO, this is a hashed triangle. So we have this parallelogram and this we have hashed triangle. So BO, where is BO? So equivalent viscous damping associated with full hysteresis loop area, okay, hysteresis loop area is equal to the same formula 1 over 4 pi over ED over ESO. So this is the formula they found, derivation of damping for special reduction. So estimation of damping and reduction of 5% damping response spectrum. At the end of the day, the equivalent viscous damping, B equivalent, instead of 5% we will add BO. This BO comes from here by changing, equating from this with Chopra book. So we have to add this BO in addition to the damping we have. So BO means hysteretic damping represented as equivalent viscous damping. This is the one. Then 5%, this is normally we have. So the term BO can be calculated as Chopra 1995 as well as 2012. We can see that. ED means this one. ED means energy dissipated by damping, and ESO means maximum strain energy. The physical significance of the term ED and ESO in equation 8.5a is illustrated in figure 8.1 11. This is figure 8.11. So just you can, if you have the interest, you can go through, but this is a basic idea because we have to know this, how we reduce it we should know. That's why I brought it here. So as you can see, this was the original seismic demand at 5%. This is our demand curve. So the reduced one, as you can see here, seismic demand for B equivalent, okay, B equivalent, BO plus 5% as we have seen. So we will reduce it and we will apply capacity spectrum and we will find the performance point. This is second period. Once you put this one, we have second period. So T is equal to 2 pi over SD over SA. This is our formula. ED, ESO, this one we already see. T equivalent is equal to B equivalent are the equivalent linear property. So B, the most important thing is B, the equivalent viscous damping. The derivation of equivalent viscous damping is very important. So this is the idea. Then as you can see, by linear idealization we have K initial, okay, this is K initial, and as you can see the other point, then this point, the first point we have AY, then the second point we have APY. We need these points, that's why I'm showing you. We have DY and DPI. We need these 2 points. We need this point, the next slide. Okay, so this is B effective. The equivalence, as you can see, what we say, the equivalent viscous damping, B equivalent. This is a formula, B equivalent. Again, using this formula, you can find AY dy, what I showed you, you see, AY, AP, A plus T. This is spectral acceleration, this is spectral displacement, there is no other thing. But dy and dp, using AY, APY, dy, dpy, because this is by linear idealization, the first point is spectral acceleration, AY, spectral acceleration. This is displacement, this is dpi. So when we come to here, using these 2 points, dpi, API, 63.7 K over API DPI plus 5. This is the formula, you see. The K factor is a measure of the extent to which the actual building stresses were represented by the parallelogram of figure 8.1. The bottom line, at the end of the spectrum, what we need is, this is the formula now, equivalent, the equivalent viscous damping. So once we know the equivalent viscous damping, so as you can see, if you have the first demand curve, if you want to reduce it, if you have 2.5 CA, you have to multiply it by SRA. Okay, 2.5 times SRA times CA. So this is equal to 2.5 times CA over BS. Again, this is for constant acceleration area. For constant velocity area, we have to multiply it with by SR, okay, SR CVT. So we need SRA and SRV. So this is SRA, this is SRV, because the curve was CV over T, but SRV is needed. So SRA and SRV, if you know SRA and SRV, directly you multiply with this constant acceleration and constant displacement curve, and we will reduce it, and we will apply your curve, capacity curve, and you can find the performance point. So this is a reduced spectrum. So you can see here, see chapter 4 of 4 for CA and CV. What is CA, what is CV? Because this will be found from table. SRA is a spectral reduction value in constant acceleration range. Yeah, it's written here in the constant acceleration range. SRV is spectral reduction value in the constant velocity range. So this is constant velocity range. So we have spectral displacement, spectral acceleration, then we can multiply it and we can find. The question is how to know the effective damping. Now, how to know the effective damping? Because if you know effective damping, okay. So we have to try iteratively until the performance point matches with our assumption. If the reduced demand acceleration displacement spectrum curve, then repeat the process. If it doesn't pass, once we reduce it and once we apply the capacity curve, okay, because I will show you what I am trying to say. Very important point, because to know the B effective, we have to know AY and DY, all these points, DPI. So once we start from that point, let's go to the next. Look, because spectral reduction factor, we have also formula, you see, SRV, SRV and SRA, we have formula. But to use this formula, we have to know B effective. This is numerically how we can drive SRA and SRV. There are also some guidelines, you can follow that. But in this formula, we have B effective, you see, we have B effective. So how to know that? Because once we apply the capacity curve and the demand curve, we have demand curve, now we reduce it, and we have the capacity curve. So by linear idealization, we have bilinear representation. Once we make the bilinear representation, this point is API. Again, the first point is AY. Then we have DY here, and here we have DPY. So we use this guess, okay? API and DPI are try performance point, and DI is displacement intersection point. the trial performance point API DPI is acceptable. If this one you have to read, you have to know that. So what I want to show you is that I will come later also. I think I have here, let me pass this one. Yeah, this is what I want to show you. Yes, look, to find the B effective to calculate SA and SV, we will start, for example, we can start from this point. For example, we will say the demand spectrum will pass this point, for example, at this point. Then we will take all these points and we will calculate B effective, and we will find SA and SV, and we will reduce our demand curve. And the demand curve, if it passes through this point, the point which we start first, if it passes through that first point, then the B effective is okay and the reduction factor is okay. But if the demand spectrum does not pass that point, then we have to guess another also. That's why it is a trial and error kind of thing. Okay, but most of the time it's recommended to use equal displacement approximation, because this one is the initial one. Just take this point and make it down and make DPI this point most of the time, then this will be the starting point. You can use it at starting point for this is bilinear idealization representation and initial acceleration displacement response spectrum demanding capacity spectrum. Extract all result structural demand from the software at this particular step. Once we know the target displacement, this is the performance point. At that point we go to our software and we can extract everything structural demand from there. So in the nutshell, what I am trying to say is that this is our building. We apply the force, then we make pushover progressively. We find pushover curve, then we change our pushover curve into spectral acceleration and spectral displacement, and we have our demand spectral acceleration in time. This is our response spectrum, and we change it into ADRA, spectral acceleration and spectral displacement. So we reduce it. Once we reduce it, we overlay it with the capacity, then demand, then this is a performance point. And once we get this point, we go to our structure, and at that point of pushover, this target displacement, we will get the displacement. But very important point what I want to show, we have seen is how to reduce, how to find SA, SV, how to find B effective and everything. Just quickly I try to show you. This is the formulas. So by doing so, spectral this is the procedure. So that is the end of it. The next one, the second one, is displacement modification application. This is the second type of finding response spectra, the target response, the target displacement. So the displacement coefficient method, as per AC 1430, AST 40, FEMA 273, FEMA 356. This one I took it from CSI because this is a modified one. Target displacement, this is a modified one. As I showed you, pushover curve is used to determine effective stiffness and pay rate, and when used with a response spectrum gives a spectrum acceleration. Okay, this is displacement coefficient method. Yeah, convert spectral acceleration to elastic displacement, to which modifying coefficients are applied to determine the target displacement. So the same thing is true. Let's go. This is a formula we are going to use, target displacement. So what we are going to do, displacement coefficient method, ATC 40, FEMA 273, FEMA 356. The displacement coefficient method provides a direct numerical process for calculating the displacement demand. It does not require converting the capacity curve to spectral coordinate, as we have seen. In the first method, no need to do that. The underlying idea is the peak elastic displacement of the equivalent single degree of freedom system of a structure can be, you see, this is elastic, not inelastic, can be modified with a series of coefficients, each account for a specific aspect of nonlinearity, to approximately obtain the peak inelastic target displacement. Once we find we have elastic single degree of freedom system, and we apply the force, and once we find the displacement, then we apply coefficients. The coefficient method is based on statistical analysis of the result of time history analysis of single degree of freedom models of different types. The demand displacement in the coefficient method is called the target displacement. Okay, so we have steps. Let's see what we are going to do. Step 1, construct a bilinear representation of the capacity curve. So we have the pushover curve, base shear with roof displacement. Then we have bilinear idealization, bilinear representation. Then we have K, Ki, Ks. So you can read what this one, the stiffness coefficients in different section of the pushover curve. This is the first step, bilinear representation in the capacity curve of the capacity curve. Okay. The second step, calculate the effective fundamental period. This is the effective fundamental period. Let me make it like this. T is equal to Ti over K, as you can see here, Ki over Ke, or I don't know, K, yeah, Ke. So this is 816, where Ti, Ki all is given. For example, Ke, effective lateral stiffness of the building in the direction under consideration. Ki is elastic lateral stiffness of the building in the direction under consideration. So Ti, this is elastic fundamental period in second in the direction under consideration, calculated by elastic dynamic analysis. So once we have the time, then we can use and calculate effective time. This is part 2. Part 3, calculate the target displacement. How? The target displacement is this one, C naught, C1, C2, C3, SA. This is spectral displacement. So spectral acceleration at TE, because we have TE here. Once we know the effective time for our building, we go here, find the spectral acceleration. You can bring from response spectrum spectral acceleration directly here. So all this one is spectral displacement. So this is effective period. For that effective period, we can bring here. C3 is to account for dynamic P delta effect. C2 is for converting elastic to inelastic displacement. This one for converting spectral displacement from here. Once we find the spectral displacement, and we will change it into multiple degree of freedom system roof displacement. So that is what we say. C2 to account for shape of hysteresis loop for hysteresis rules. So multiplying these all coefficients, you can find target displacement. This is very easy compared to that one. And we have a lot. If you want to read what is T, what is CO, C1, TO, R, what is R factor, C2, C3, SA, W, everything is given in the code. This is all definitions, so you can go through. We have also CO, C2, different tables, charts, so we can find from there. So that is in 1996. FEMA 440 came in 2005, as I discussed, as I informed you at the beginning of this demonstration. So improved nonlinear static procedure. They improved it. So what they improved, just in the nutshell, they make a lot of experiments in single degree of freedom system, and they came up with this hysteresis loop force displacement, elastic, perfectly plastic, and stiffness degrading SD. This is also they came with strengths and stiffness degrading hysteresis type, nonlinear, elastic. All these kind of things are in the improved one. This is side class, elastic, perfectly plastic. Mean they make a lot of experiments and they came up with different R values, approximate, the approximate, and they make, this is all the experiment they did from the improved version. And the most important version is you see there is no C3 here. So in the coefficient method they just remove C3, and the TE calculation, C2 calculation, and the target displacement calculation, everything is changed. C1, RY factor, again here idealized force displacement relation, determine these values, KE, VY, everything is, this is in the new version. So no C3 term is included here, and the expression for C1 and C2 is changed in the nutshell. So you can go through and check what is the change they came up with. So optimal equivalent linear parameter, effective period, T effective and effective damping, this is also the change, are determined through a statistical analysis that minimizes in a rigorous manner the extreme occurrence of the difference error between the maximum response of an actual inelastic system and its equivalent linear counterpart. New expression for effective period and effective damping are proposed. So equivalent linearization method is not included in ASC 4113. Instead, the displacement coefficient method is the only nonlinear static procedure prescribed in ASC 4113 and onward. Okay, so improved equivalent linearization, please go through. This is the formula. They add A, B, C, D terms, and we have just I brought it here to show you. We have table also. This all for the effective period also changed. This is a change formulas. This is GH, IJ, blah blah. Here, as you can see, I, GH, every coefficient and everything how to calculate. They came up with this formula. So modified ADRA to use T secant also. This is also changed. Please go through and read it. We don't have time here now. Modified ADRAs to use TS also. They change this also. A spectra reduction, you see the B also changed. So go through just for our demonstration purpose. That's enough. The non-linear response history analysis, non-linear response history equivalent single degree of freedom system. Single degree of freedom system. Determining the performance point using this is the third part, because the two parts were finished. The third part, as we discussed, you have pushover curve, came from your multiple degree of freedom system. You change it, idealize it, make a static rule, apply this static rule to your single degree of freedom system, then directly shake the building with a earthquake and pick the maximum displacement X are inelastic. Take this point, go to your original structural demand at this point. So this is your demand. So find all the demand of extract here. So all extract all results structural demand from the software at this particular step of pushover analysis. Once you know the target displacement, then your building, you can extract everything from there. Okay, pushover analysis advantage and disadvantage. It requires less computer time compared to dynamic analysis. Pushover curve can provide the lateral capacity of the building and expose the inherent strengths and weakness of the structure. It can provide useful information on the effect of changing the strengths and stiffness. Disadvantage: consideration of only one-dimensional static load, only one first load pattern, first mode. This is consideration of only one failure mode, first mode. It doesn't consider any higher modes. It does not account directly for the dynamic nature of earthquake load. That means inertial force not considered. This is static. It does not account directly for the hysteretic loop. Hysteretic energy dissipation and stiffness degradation are considered only indirectly, as we have seen. It works well if the structure responds in essentially a single mode of vibration. Higher mode effects are neglected, as we have seen. There is no higher mode. It is less accurate and possibly inaccurate for tall buildings. That's why we are going to multi-mode based seismic analysis procedure. So that one was single mode based. Until now we have seen single mode based pushover analysis. Now very quickly let's see multi-mode based single degree of freedom, multi-mode based single seismic analysis procedure. What does it mean? So multi-mode pushover analysis procedure, we have this pushover analysis procedure, as we have already discussed first mode inertia. But multi-mode analysis, we have how many? Modal combination of loads, modal combination of responses, consecutive modal pushover, and adoptive modal pushover. And these are all the researchers and whatever they do, and we will concentrate in modal pushover, multi-mode pushover analysis. This modal pushover analysis, Chopra and Goel 2002 they propose, and we will concentrate in this one, modal combination, and we have two types. We will see. So what is modal combination of loading, and all the point I just put it here. So modal combination of loading, what we do is that based on the combined load pattern, based on different modes, we carry out the pushover analysis and calculated the response. So we use load pattern which represent more than one mode. So we are not applying only one mode, but we are applying lots of mode, and we combine the load and we apply the load, and we carry pushover analysis, and that is modal combination of load. So what we do is that based on the combined load pattern, so we will find the combined load pattern from different modes. On different mode we carry out the pushover analysis and we calculate the response once we find the target displacement. The second one, modal combination, this is proposed by Kalkan and Kans 2004, Jan, Subul and Gunai 2010. This is the second one, modal combination of response. Modal combination of response, here we apply each mode separately and we combine the response corresponding to each mode using SRSS or any other combination rule. So what we are doing here, we simply apply the loads, the modes differently. Mode 1 load first, then mode 2, mode 3 and mode 4 differently, and we will SRSS to find the we use combination rule, CQC or SRSS or other combination rule to find the response. The third one, consecutive modal pushover analysis. These are the researchers. Modified CPM analysis. What they say, this one is based on the idea that load pattern can be changed within the same analysis. While you are doing the same analysis, we can change the load. For example, first apply the first mode pattern, shape, force, and then during the same analysis, after some target displacement, change the second mode shape pattern in the same analysis. So from the same analysis you get the overall response, which is expected to the contribution of from all modes. So the difference is this one, we apply the modes differently and we SRSS the result. But here we will apply the modes in the same analysis at the end of the day. That is what it says. Adoptive mode pushover. These are the researchers, and what they say, the overlying idea. The idea is that the structural properties, the mode shapes, and the load combinations all can be changed during the analysis. While you are analyzing, you can change the structural property, the mode shapes, load combination, everything. So the modal property of the structure is modified in the real time during the analysis to account for the inelastic action in this approach. So that is what the 4 multi-mode pushover analysis says. So let's go here. Why we still need approximate seismic analysis procedure? So approximation means pushover. Despite the development of fast computing tools, software and other advancements, the detailed nonlinear response history analysis is still a difficult task for several reasons. The first one is ground motion. In the first class, this linear time history analysis, how to extract, modify, scaling, modeling, everything we discussed there. So that is one part. Compatible with seismic design spectrum for its so finding ground motion is very difficult, computationally demanding in elastic modeling, 3D analysis to account for completing between lateral and torsional motions, subject to two, because we have to apply x and y in the two, this is as per code, we have to apply in two directions. That is also another point. Must be repeated for several excitations, because we minimum as per code we need 7, but for our research I use 11. Structural model must be sophisticated enough to represent a building realistically, especially deterioration in its strength at large displacement. So approximate method are still an attractive option. Pushover analysis is an attractive option as an alternate to the rigorous nonlinear response history analysis procedure. But for our, we will do both to see the difference. So effective earthquake force on an multiple degree of freedom system. In order to develop those two procedures, we can start with effective earthquake force for any multiple degree of freedom system. So we have two types of pushover analysis here also. The uncoupled modal response history analysis, UMRHA, and the modal pushover analysis. We have two types. So we will see how. So to develop these two methods, let's continue. This is the governing equation of motion of the elastic multiple degree of freedom system. We have seen this in the formulation of the governing equation of motion in the time tree analysis as well as response tree analysis. We saw that subject to earthquake ground motion. So we have here mu dot dot c mu dot plus ku damping this stiffness and inertial part. This is equal to minus m, this is 1 ug dot, this is p effective total. So where the effective earthquake force is equal to this one. Now what we are going to do is we are going to introduce the new concept other than what we discussed in the first video. We are going to introduce the spatial distribution of those forces over the structure is defined by the vector this one. So let's change m times 1 into spatial distribution, and we use this concept to generate these two UMRHA procedure, and the modal pushover analysis procedure is based on this, because for each mode you will not maybe you will not understand me now what I am saying, but once we have P effective, this P effective total came from each mode: first mode, second mode, third mode, fifth mode. So all mode effective earthquake, then summation of all mode effective earthquake will be total effective. But for each mode we will have P effective first mode, P effective second mode, P effective third mode, because the contribution of higher mode is included. Then this one, the spatial distribution, we will use it for each mode for the distribution of P effective of each mode. I think I explained it properly. So that is how we are going to do. So once we have the first mode and we have P effective first mode, and we will use the distribution, spatial distribution for each floor. So the first mode have, second mode have, third mode will continue like that. Then we will add up and it will give up P effective. I will show you there is a lot of experiments was done about what does this mean. What does it mean? So the idea of modal expansion of excitation vector PT of the form PT is equal to S times PT. So what we are going to use, this is the very important concept, modal expansion of excitation vector PT, S times PT. That means we are dividing it for each mode. So each mode will have its own PT, first mode, second mode, third mode, fourth mode, and each mode will have the spatial distribution S, and the force will be distributed each floor. So the summation will become the total P effective. It will give us total P effective. So the primary idea is to extend the vector S as S is equal to summation of R is equal to I from 1 to N. SR. This is SR means for each floor. Okay. Basically this is for each mode. Okay, for each mode from I to N. So R is 1 I from N. So we have modal participation, this is we have modal participation factor times M times phi R. So S total is equal to this one. So for each mode now, modal participation factor for mode 1, mass for each floor, then phi will be for each story. So this one for only first mode, then second mode from R to N mode we have, then it will give us total S. This is a very important concept. So this equation may be viewed as an expansion of the distribution S of applied force in terms of inertial force distribution SR associated with natural modes, because we have this modal shape. Multiplying both sides of the above equation with orthogonality property, I explained what orthogonality property is, what is of diagonal parts will be 0 and only the diagonal parts will be modal masses and stiffness, everything we discussed it in the second video. I recommend you to choose that. So when we multiply this with phi transpose, at the end of the day, at the end of the spectrum, we will find this formula: Rn is equal to phi n ts over mn. Then the contribution of n's mode, to S, to the total S, will be Sn. So that means the total effective force will be distributed to each mode: mode 1, mode 2, mode 3, mode 4. Then each mode will have also a contribution into distribution into each floor. So Rn m phi n. So this is for nth mode only. Then the total will become S. I think you get my point. So P effective is equal to m times 1 as we discussed. So m times 1 is S times UG dot co. This force distribution can be expanded as a summation of modal inertial force distribution. So modal expansion of spatial distribution. So S, we have Sm times 1 Sn. Sn is for only one mode. If you have 5 mode from 1 to 5, then each mode will have Rn m times phi n. Then this will be for each mode for each floor, where Rn is Ln over Mn, Ln is equal to phi n, this transpose m times 1, Mn is equal to phi transpose m. This is all the derivation. So the effective earthquake force can be expressed as, you see, total P effective is equal to P effective for nth mode. Nth mode. That means mode 1 have its own P effective. It has contribution very easily. It has contribution. So N1 up to N. P effective NT. So N1 unto N minus Sn UG. So Sn means the distribution factor. So the combination, the contribution of the nth mode to P effective T and S are P effective N is minus Sn UG dot com. So Sn means Rn m times phi n. I will show you this one. Modal expansion of the distribution Sm times 1 of effective earthquake force. This will be very easy. So P effective total is this one, but we have contribution. So the first mode has contribution, the second mode has contribution, the third mode has contribution, the fourth mode has contribution, and the fifth mode has contribution, and it continue like that. Again, S1 has a distribution, you see, for each floor. So the direction of force Sjn at the j's floor level is contributed by the algebraic sign of phi ji. This is mode shape. Jn, the nth mode. The j's floor displacement in the mode phi n. So the main idea is this. P effective total has contribution from different modes, and we have a special distribution S. So this S1 has the P effective mode 1, P effective mode 2, and so on. So this is a very underlying idea we have to know to generate this modal expansion of the effective earthquake force. Once we know this, then utilizing the modal expansion of P effective T and S for each mode, two procedures for approximate analysis of inelastic buildings are proposed by Chopra and Goel. So Chopra and Goel, with the idea of modal expansion of effective earthquake forces, they came up with two methods, two approximate methods for pushover analysis. The first one is the uncoupled modal response history analysis, and the second one is the modal pushover analysis, MPA. So you have UMRHA and we have MPA. So we are clear now. So because of this expansion, modal expansion of the effective earthquake force, we have two procedures, UMRHA and MPA. The uncoupled modal response history analysis and the modal pushover analysis. Not intended for particular application, the UMRHA procedure is developed only to provide a rationale for the modal pushover analysis, but as now it's also used. Most of the time we use the modal pushover analysis, but UMRHA also we will see. At the end of the day, with different research and everything, they found out that it is important. We can use it also. In the UMRHA procedure, the response history of the building to P effective in nth mode The nth mode component of the excitation is determined by the nonlinear response history analysis of an elastic single degree of freedom system and superposition of this modal response give the total responses. So in the UMRHA procedure, what it says, we have single degree of freedom system, okay, an elastic single degree of freedom system, and we apply direct nonlinear response history analysis to it, and we will extract the responses and we will sum it, response by total responses. So the UMRHA procedure, the response history of the building to P effective for the first mode, second mode, third mode. So we apply the first mode and we will do, then we will apply second mode force, and we will then at the end of the day for the first, second, fourth, fifth mode directly we will add up the responses. That is what it says. It is the same as classical model analysis, but here the linear single degree of freedom is changed to inelastic single degree of freedom system. The idea of classical model analysis is applicable to linear system, but in UMRHA the idea is extended as well. So it is the same classical model analysis, but the idea is extended for non-linear single degree of freedom system as well. So the only thing is we will apply nonlinear response history analysis directly the earthquake, the expected earthquake, and we will extract the responses for single degree of freedom system for each mode, and we will sum. In the MPA modal pushover analysis procedure, the peak responses to P effective n's, as we discussed for the nth mode, is determined by the nonlinear static or pushover analysis, and the peak modal responses are combined by modal combination rule to estimate the total responses. So the only difference is for the modal pushover analysis, for the nth mode we will incrementally we will add the force as we have seen in this video, and we will extract the responses for each mode. Then we will SRSS or any combination rule to find the responses. Here in this procedure, the pushover analysis performed for each mode separately, which with modal inertial load pattern for that mode, and then we combine the peak responses using SRSS or any other combination rule, just like response spectrum analysis. So this is the copy of response spectrum analysis, and UMRHA is the same as classical model analysis. Let's continue. Both of them are based on the idea that the modal expansion of P effective total earthquake force, that the modal expansion can be performed for each mode, and the response for each mode can be separately calculated and then combined at the end to get the total response. Based on this idea, two methods are developed by Chopra and Goel. So this is very important point to discuss. As we have seen here, this is the idea. P effective, whatever P effective you have at the base, is a contribution of different modes, and for each mode we have S special distribution, and that is the idea of UMRHA or PMA, MP, the modal pushover analysis. Okay, now let me quickly go through UMRHA. So the uncoupled modal response history analysis, as we have seen, what we are going to do is we are going to perform nonlinear time response history analysis on our nonlinear single degree of freedom system, and pick the responses for each mode, mode 1, mode 2, mode 3 separately, and we will add. Then let's see. UMRHA procedure, this is classical model analysis procedure. The same is true for the uncoupled modal response history analysis UMRHA procedure. Instead of linear single degree of freedom system, now we are going to use nonlinear single degree of freedom system. As you can see, from where we will discuss this one, because we will perform monotonic or cyclic pushover analysis, and we generate pushover curve. Then we will idealize that pushover curve and with bilinear curve, and we will assign it to our nonlinear single degree of freedom system. So for first mode, we will have one first mode idealization curve. So when we perform second mode, we will have second mode idealization. So we cannot use the same curve for each mode. So we have to perform cyclic pushover analysis for each step. So first mode, we have first mode shape. We will add it. We will apply it in our multiple degree of freedom system, and we will make pushover analysis. Let me show you, just to remind you. This is our multiple degree of freedom system. So we will apply our first mode shape, and we will apply the load progressively. Then we will get our hysteresis curve. This pushover, this is our hysteresis curve. Then we will have the backbone, and we will have our force deformation curve. So as you can see, for the first load pattern, we have different. Then for the second mode pattern, we have different hysteresis. For the fourth mode, then so once we get this, we will idealize it, and we will apply it into our nonlinear single degree of freedom system, and we will apply the ground for motion earthquake. Then we will extract the response, and we will add the response. So that's how we are going to do it. So this is mode 1, mode 2, mode 3. So for mode 1 we have different, for mode 2 we have different, for mode 3 we have different. Then we will apply the earthquake, and we will collect the responses, and we will add the responses, and it will give us our multiple degree of freedom system. Okay, so the uncoupled modal response history analysis procedure, it is the same as classical model analysis, but let me go through it very fast. Linear elastic, when now we have nonlinear model, but for linear elastic analysis, the classical model analysis procedure for linear elastic system is equivalent to finding the response of the structure, the P effective n total for each n mode, and superposing the responses for all n. That was classical model analysis. Okay, the same is true. The response of the system to P effective n mode is entirely in the nth mode only, with no contribution from other mode. There is no contribution from, for example, if we are doing for first mode, there is no contribution from second mode or third mode, which implies that the modes are uncoupled, because for classical model analysis we have two ways we uncouple it. The question, we're using orthogonality property, and we are using for that mode separately. That's what we did. The equation governing the response of the linear elastic multiple degree of freedom system to P effective nth mode will be, this is the equation we have seen. We have a special distribution also, and the resulting floor displacement using the idea of modal expansion from modal analysis are un is phi n times qn. From q coordinate, by multiplying it with modal shape, we change it into u coordinate to find the equation. This is also modal expansion equation concept for from modal analysis. So substituting un in governing equation and pre-multiply by orthogonality property. This orthogonality property by phi n transpose leaves the equation governing the modal coordinate qn. This is the final equation we have. This is the final equation for the nth mode, where omega n is a natural frequency, xi n is a damping ratio, and modal participation factor is the modal participation factor for the nth mode only. So this is uncoupled equation of motion, general uncoupled equation of motion. As demonstrated in classical modal analysis, the solution of nth mode equation of motion, so Qn we have Rn times dn, displacement, where dn is deformation response of nth mode linear elastic single degree of freedom system governed by this equation. So therefore un Rn times phi n times dn, because here we have phi n Qn, so un will be phi n times Rn, so Qn will be changed by Rn times dn. This is for displacement, and for drift just phi upper and lower story will be the subtract and times dn. The above equation represent the response of the multiple degree of freedom system to P effective for nth that mode only. There is no other addition from other mode, and superposing the response for all n, it will give the response of the system due to total excitation P effective total. We are 198, yeah, here. So if you add all, it will give us the total P effective. I hope you understand. So this is Rn, means that is Rn for each mode, from 1 up to n modes. So the UMRHA procedure for exact analysis of linear elastic system is identical to classical modal response history analysis, all the same. But to drive this equation, now we have used the modal expansion of a spatial distribution of effective earthquake force, S. We use S, but it is all the same. It is all the same. In the classical model analysis also the same, but that is the only difference. The uncoupled modal response history analysis procedure, just let me go through. In inelastic system, although modal analysis is not valid for inelastic system, its dynamic response can usefully be discussed in terms of the natural vibration modes of the corresponding linear system. Each structural element of this linear system is defined to have the same stiffness as its initial stiffness in the inelastic system. Both systems have the same mass and damping. Therefore, the natural vibration period and modes of the corresponding linear systems are the same as the vibration property of the inelastic system undergoing a small oscillation, which are referred to as periods and modes of the inelastic system. So, thus the modal expansion of effective earthquake force is also valid for inelastic system, where phi n now represent the modes of the corresponding linear system. So this is the underlying idea. Now, the uncoupled modal response history analysis. What the Chopra says, the earthquake governing the response of the inelastic multiple degree of freedom system to P effective, the nth mode, this is the formula as we have found. The solution of this equation will no longer be described by un is equal to phi n times qn, because modes other than the nth mode will also contribute to the system response. So even if it is uncoupled equation of motion, now there is what it says is other than nth mode, for example, from other than first mode, the second mode and the third mode has contribution. So the solution, because this is an inelastic system, the solution of this equation will no longer be described by this, because this is uncoupled. From q coordinate we take it to u coordinate by multiplying with mode shapes. But in inelastic system there is contribution. This is no more uncoupled. That is the idea. So because mode other than the first the nth mode will also contribute to the system response, implying that the vibration modes are now coupled, not decoupled. Thus the floor displacement are given by un is equal to phi r qr from first mode to nth mode. So each mode has contribution from other mode. However, because for linear system qr is equal to 0 for all modes other than the nth modes, it is reasonable to expect that qr may be small for inelastic system. This is the underlying idea, implying that the elastic modes are at most weakly coupled. So by this is what they say. For elastic system it is known that once we use the orthogonality property and we just from the coupled equation of motion we change it into uncoupled equation of motion for each mode and for each floor. So each equation, uncoupled equation of motion, can will be contributed only for that mode. For each mode we will have that. Then we will have the equation with the degree of freedom system equal to the degree of freedom system. So this is just like the linear system. Once we use this assumption, this is the assumption now Chopra did. Once we approximately the displacement is equal to, not equal to, approximately equal to phi times qn of t, just like linear system, now we are ready to go. So qu is replaced by any nonlinear function fsu. Sn is a special distribution of nth mode shape. We ignore it and assume it like the linear system. Other mode contribution assumed to be small enough to be ignored. So this is the underlying idea which Chopra and Goel assumed for UMRHA procedure. So they did experiment. For example, this is mode 1, this is mode 2, this is mode 3, and this is mode 4. For each single degree of freedom system, when they apply mode 1, when they use mode 1, they perform cyclic pushover analysis or monolithic pushover analysis, and they found pushover curve, they idealized it, and they make hysteresis curve, and they apply that hysteresis curve into equivalent non-linear single degree of freedom system. And when they apply the ground motion, then for the first contribution, P effective first mode, you see the contribution is only in the first mode. Even if there is contribution from for example, sorry, we have to go like this. Even if there is contribution from second mode, third mode, fourth mode, but the contribution is very small compared to the first mode. For example, in the second experiment, the second mode has the highest contribution. The other is very this is, you see, second mode effective force. Again, the third mode is the same, and the first mode is the same. So it is reasonable to assume that approximate that the other modes, higher mode contribution is 0. I mean, it's not 0 as you can see. It's not 0, but it's very small compared to that mode. So this is underlying idea, and this is the experiment. Figure shows that the roof displacement due to the force vector P effective in the nth vector in the nth mode is due to primarily to the nth mode only, because this is first mode only. The first mode is dominated here. This is the second mode, this is the third mode, and this is the fourth mode. but that other mode contribution the response. The second, third, and fourth mode start respond to excitation the instant the structure first yield. Although the natural vibration modes are no longer uncoupled, even if no longer uncoupled, if the system responses in the inelastic range, modal coupling is weak. So this is very weak, as you can see. So that is the idea. Now, as per this experiment, Chopra and as per this experiment, Chopra and sorry, I don't know what. Okay, sorry. When I just want to delete this. Okay. So this weak coupling of modes implies that the structure response due to excitation P effective ends mode, the ends mode only, may be approximated by. Now the displacement of the structure UT can be taken approximately from Q coordinate using modal expansion, multiply it with phi, then you can find the response of multiple degree of freedom system. Substitute this approximation into governing equation and pre-multiply by this phi transpose means modal. Based on the above assumption, we get the uncoupled equation of motion just by multiplying with the phi theta. I explain this step by step in the classical modal analysis. You can refer first video how we came up to this equation. So based on the above assumption, we get the uncoupled equation of motion. Now we get the uncoupled equation of motion, where FSM is a nonlinear hysteretic function of the ends mode coordinates Qn. So for Qn we have Fsn. So Fsn is equal to Fsn Qn. This will be phi n transpose times Fsn Qn. If the smaller contribution of other modes had not been neglected, Fsn would depend on all mode coordinates, and the set of equation would be coupled because of yielding of the structure. But now we don't consider the higher modes. By comparing the ends mode governing equation of motion with linear counterpart from linear classical analysis, the solution can be expressed as Qnt is equal to Rn dnt, where dnt is now governed by this equation. This is our final equation of motion for the ends mode of inelastic single degree of freedom system. So we know Fsn is for each mode. Now we have phi transpose times Fs for Qn. So this is the final equation motion. Dn may be interpreted as the deformation response of the ends mode in elastic single degree of freedom system as single degree freedom defined by. Now our single degree of freedom system also defined by a small oscillation vibration property, natural frequency, natural period, and damping of the ends mode of the multiple degree of freedom system. So this comes from cyclic pushover analysis for that mode. If it is first mode, for first mode, second mode, second mode, third mode, third mode. So this single degree of freedom system, the behavior of inelastic single freedom system will be the same as multiple degree of freedom system. The force deformation relation introducing the ends mode inelastic single degree of freedom system permitted the extension to inelastic system of the well established concept for elastic system as well. So once we get, we will assign it. The solution of the nonlinear modal equation provides dnt, which can be substituted into the following same equation to obtain floor displacement and story drift. Now we have, this is floor displacement and we have story drift. This equation approximates the response of the inelastic multiple degree of freedom system for that P effective nth mode contribution toward the total P effective. Superposition of responses, P effective total is equal to now the addition of all provide total response to P effective. So this is RNT is equal to for first mode until n mode. This is the URMHA procedure for approximate analysis of inelastic system. So in the nutshell, very shortly, this is what UMRHA means. So this is directly the same as classical model analysis. So for the test, sorry, we have discussed this also, to test the modal uncoupled approximation in UMRHA. The response of the 9-story building to P effective total is equal to, for each mode, as you can see, is determined by 2 meters and compared. So as you can see, nonlinear response history analysis, this is directly we will apply the ground motion to the nonlinear single degree of freedom system. Nonlinear single degree of freedom system directly, and we will pick the peak result. We will find maximum and we will go to the pushover curve and we will find the demand of the UMRHA. As I showed you, for each mode it is separated, and we will perform cyclic pushover analysis or monolithic pushover analysis for multiple degree of freedom system, generate pushover curve, idealize it with bilinear curve, and we will assign it as stiffness to nonlinear equivalent nonlinear single degree of freedom system. Then we will perform the analysis and we will pick the responses for that mode. For the second mode also we will apply the second mode load pattern and we will perform the same procedure, cyclic pushover analysis. Then we will get the pushover curve, and from the pushover curve we have to idealize it and we will assign the hysteresis map, force deformation curve, and the hysteresis rule for our equivalent non-linear single degree of freedom system, and we will perform dynamic analysis and we will find the result. So in the UMRHA we have a chance to see the contribution of the total response, because each mode we will perform separately, but in nonlinear response history analysis we don't have that chance. We will find only the peak response. Okay, so this one we will perform for each mode and we will add up and we will find the total response. But for response history analysis we will not get that. We will find only the maximum. So as you can see, RHSA procedure analysis and UMRHA procedure analysis, the result is almost the same. The result is almost the same, not that much different. This is for story. This is story drift, and this is displacement. So the result is the same. So the summary of slide. The last slide confirmed that the assumption the modes can be still considered uncoupled and the idea can be extended to an elastic system may not result in significant error in the overall estimation, as we have seen. But the benefit is that UMRHA will be able to give us the individual mode contribution for each mode, as I have said now, and the total nonlinear response history analysis will not be able to give this decomposition or individual contribution. But UMRHA, if you perform, it is very tedious, time taking, but if you perform UMRHA, you can get individual contribution from first mode contribution, second mode, fourth mode, and so on. So this individual contribution can be used to effectively understand the dynamic behavior of inelastic behavior of the structure. So UMRHA and nonlinear response history analysis procedure are almost the same result as per Chopra and Goel research. That is what they do. So as per our discussion, this is what we see. UMRHA procedure, you have multiple degree of freedom system, then you perform cyclic pushover analysis in your multiple degree of freedom system, then you capture the base shear and the roof displacement. This is your, then construct cyclic pushover curve for each mode. For the first mode, you have first mode cyclic pushover curve. For the second mode, we have second mode cyclic pushover. For the third mode, we have third mode cyclic pushover. So for each mode, we have to generate different cyclic pushover curves, and we will idealize it into idealized hysterical model. This is Fs over Li di, force deformation curve. Once we idealize it with the backbone, you see this is a backbone curve, then we will assign it to our single degree of freedom system, nonlinear single degree of freedom system. So this is our equation of motion. Then we will apply the ground motion. And we will find di and fli. This is what we need, di and fsli for single degree of freedom system. Then once we get the single degree of freedom system, then we will change it into multiple degree of freedom system, because the behavior of nonlinear single degree of equivalent single degree of freedom system is the same as multiple degree of freedom system. So we convert it to force deformation behavior to solve that equation. This is our coupled, now uncoupled. This is uncoupled equation of motion for each mode, and assign it to nonlinear single degree of freedom system. Repeat the process for second mode, again third mode, fourth mode, whatever mode you have. So this is the overall idea. We perform cyclic pushover analysis for each mode, like 1 to 4 modes if you think the 4 modes are significant. Then construct cyclic pushover curve, then convert it into idealized hysteretic model like this. Then assign it to single degree of freedom system for the mode, then apply the ground motion, and then find the individual single degree of freedom response system, then change it into multiple single degree of freedom. For this one, Perform 3D will perform it. Once you have I will show you, I show you lots of time, but once you have your nonlinear multiple degree of freedom system, then you apply first mode, then it will capture for you the pushover curve. Again, once you finish this one, change it into idealized force deformation curve, then apply it into your equivalent single degree of nonlinear single degree of freedom system. Continue your analysis, then apply the ground motion and capture the responses. Once you get the responses, change it into multiple degree of freedom system. That is the idea. So in ETABS, I didn't find this thing, but Perform 3D, I think it will perform for you, just if you use manual calculation. But I will show you this time softwares are very easy. Okay, the overall procedure of UMRHA procedure. UMRHA procedure. So the overall idea, we perform cyclic pushover analysis for each mode. then construct cyclic pushover curve, then convert it to idealized hysteresis model, as I showed you with perform 3D, then assign it to nonlinear single degree of freedom system for that mode, then apply the ground motion to this nonlinear single degree of freedom system. Directly you have single freedom, apply the any ground motion, lenders or whatever you extract from peer website, and but you have to scale it, match it, and as per your target response spectrum, and then calculate the responses, then convert them to structural response, and then sum them to find final response, because in the UMRHA you have to sum directly, no CQS or something. That will give us the overall inelastic response as well as individual modal response. Okay, this is sample cyclic pushover analysis. So I think we have seen it in the first slide. So we perform cyclic pushover analysis, we normalize it with the building weight, and we normalize it with the height. We have cyclic pushover and monolithic pushover. This is monolithic only for first mode, or only one mode, no cyclic. Cyclic means you apply it in this, then in the negative, in the positive side. Monolithic pushover in negative, this is monolithic pushover in the positive. So once you get this in the perform 3D, it will give you the performance of each component of your structure. For example, in this level, brick wall begin to crack. In this level, shear wall begin to crack. In this level, shear wall steel reinforcement bar begin yielding in tension. So it will give you the performance of your building as per your force deformation curve and the hysteresis rule you gave to that element. Once it passes the limit, the ductility, then once it passes it, then it will notify you, because the capacity of your building will be given first. That is the beauty of nonlinear response. So the cyclic behavior of some example buildings, this is also thus behaviors can be converted into force deformation behavior. So behavior, and we can assign it to nonlinear degree of freedom systems, and we can solve that mode. So this is mode 1, mode 1, mode 1 for different building, mode 2, mode 2. This is the roof displacement. Yeah, all this is hysteresis curves performed. This is Professor Fouad. They perform this, and once they got the hysteresis curve, force deformation pushover curve, they will change it into idealized bilinear or trilinear idealized curve, and we will assign it to our single degree of freedom system as a capacity. Then demand to capacity ratio will be checked at the end. So this is also the same for 20-story building. We have base shear. This is normalized base shear with W. This is normalized roof with H. This is our single degree of freedom system. So what they did is, this is multiple degree of freedom system where they find hysteresis loop, then they idealized it first. Then this backbone is given as K, assign the force deformation curve as nonlinear single degree of freedom system, and apply the ground motion to your single degree of freedom system. Then the response will match to your multiple degree of freedom system. You see cyclic pushover done in the multiple degree of freedom system. Then this, the red one, is the response of single degree of freedom system under ground motion. So when the ground motion applied to single degree of freedom system, almost it will match. It will match. So the your single degree of freedom system is the can capture the behavior and the property of your multiple degree of freedom system. This is what UMRHA is. This is also idealization of cyclic pushover curve for few example building. This is also the same. They apply cyclic pushover curve. They found the hysteresis loop pushover curve. Then they assign it. After they idealize it, they assign it to nonlinear degree single degree of freedom system. Then they apply the earthquake or any load pattern for your building. Then you see all the experiment, they found it. So if force deformation curve match well, so that means our non-linear single degree of freedom system can capture the first mode for our real multiple degree of freedom with a reasonable accuracy. This is also idealization of cyclic pushover curve. This is also the same. Mode 2, that is for mode 1, I think. This is for mode 2, they did the same and they found with the experiment. So most experiments, they show that this is mode 3, they idealized it. So the idealization of cyclic pushover curve, this is the same thing what we have discussed. This is multiple degree of freedom system. Apply cyclic pushover curve, then idealize it, apply it with single degree of freedom 1, single degree of freedom 2, single degree of freedom 3, then apply the force and perform dynamic analysis on your idealized equivalent nonlinear single degree of freedom system, then apply it and capture it and it will match. So again with experiment, modal decomposition of nonlinear response using UMRHA procedure. So as you can see, 44 story case study building in strong direction example. So what they did here is mode 1, mode 2, mode 3, this is from UMRHA, and this is the peak envelope of combined history, because they add up all this. Again, peak interstory drift, this is peak displacement, this is peak interstory drift, again from mode 1, mode 2, mode 3, and this is the peak one. So hence the response of each nonlinear single degree of freedom system is converted into a response of multiple degree of freedom system and compared in a graph form. So first mode, second mode, third mode, then it will be converted into multiple degree of freedom system. As you can see, 45 story, and this is the envelope combined history. Again, this one, modal decomposition of nonlinear response using UMRHA procedure. This is also the same. This is story shear, this is moment, this one is displacement, this is interstory drift. Then now the comparison, if you perform UMRHA versus nonlinear response history analysis, as we discussed, I will say it again. UMRHA means you perform cyclic pushover analysis in your multiple degree of freedom system, capture the pushover curve, idealize it into idealized force deformation curve, then apply it into your equivalent non-linear single degree of freedom system and perform dynamic analysis and capture the response for first mode. Again, apply second mode pattern, perform cyclic pushover analysis, then continue like this and go until 5 or 4, 6 modes and add up the result. Then this is the blue one, is the UMRHA procedure. But for nonlinear response history analysis, you have single degree of freedom system, directly apply dynamic analysis and find the result, that is, and change it into multiple degree of freedom system. So the result, as you can see, not that much far. So UMRHA and but the use of UMRHA or the advantage of UMRHA over a nonlinear response history analysis is you can see each mode response, the effect of each mode, the contribution of each mode toward the total. But in nonlinear response history analysis, you don't have that chance. Directly you will find the peak. But in UMRHA, to find the combined 3 modes, you have to perform each mode in the cyclic pushover analysis each time. So that is the advantage. So this is also modal decomposition of nonlinear response using UMRHA procedure. As you can see, this is UMRHA for displacement, inter-story drift, story shear, moment. So this is also the same. So as you can see, the result from nonlinear response history analysis is this one. UMRHA combined is the blue one. Individual modes are this one. So there may be mode 1, mode 2, mode 3, but you combine it into UMRHA blue color, and you can compare. This is also the same. This is individual modes, and this is a combined modes. This is from nonlinear response history analysis. By doing so, you can see the result. This is also the same. This is also the same. So modal decomposition of nonlinear response using UMRHA procedure. So as you can see, mode 1, mode 2, mode 3, the response roof displacement, roof displacement, roof displacement, mode 1, mode 2, then combine it, and this is ground motion from response history, nonlinear response history analysis. Then the result is almost the same. So UMRHA and nonlinear response history analysis are almost the same. The uncoupled modal response history analysis procedure, we already discussed it, but for elastic system, UMRHA is the same as classical modal response history analysis, an exact analysis procedure we have seen now. For inelastic system, UMRHA is approximate analysis procedure, because we approximate that the contribution from higher modes is 0. So we approximate it, and we make the equation uncoupled. That's approximation. The UMRHA for inelastic system is based on two approximations. The first one is superposition of responses, a strictly valid only elastic system, but we use it approximately valid for inelastic system also, because we super from mode 1, 2, 3, 4, 5, 6, and we will add it, neglecting the coupling of modal coordinates, because we just assume that, which permitted computing the response of inelastic multiple degree of freedom system from each mode from that of a single degree of freedom system. This approximation is reasonable only because the excitation is P effective in nth mode contribution to the total excitation P effective. So this modal expansion modal expansion concept, it would not be valid for an excitation with lateral force distribution different than SN. SN, we have SN, so only for that mode it works, the total excitation P effective, pointing out that the modal expansion, this is the modal expansion of effective earthquake force, is a key concept underlying the UMRHA. So this is very important point. The modal expansion concept P effective for each mode, and each mode will have its own distribution factor for each floor. This is what we discussed. Okay, that is the end of it. Now let's quickly consider the modal pushover analysis, MPA procedure, Chopra and Goal, 2002. By using the concept of UMRHA, what we discuss now, procedure for the development of modal pushover analysis, So we will use the concept what we have discussed until now for the development of modal pushover analysis by Chopra and Goel. So overall procedure of modal pushover analysis, just like UMRHA analysis, let us see the elastic and inelastic system separately. For linear system, the modal pushover analysis is based on the idea that we can apply the effective earthquake force of any nth mode separately to each structure, and we don't apply it just once, but in a progressive pattern, pushover pattern, because we have different steps to construct the pushover curve, and we keep on increasing it until the target displacement for that particular mode reached. So for that particular mode reached, we will push it with progressively, not one time. So the same concept we are using UMRHA, but the only difference is the load is progressive. So for that ends mode, we don't apply it once like UMRHA, but here we will apply it progressively. That is a difference. And we extract the modal responses for that particular mode. Then we combine it with other mode responses to get the overall response of the structure. So we will combine it. First we apply the first mode progressively, then the second mode progressively, the third mode progressively, and we will construct pushover analysis and this pushover curve, and we will idealize it. We will change it into hysteresis curve, and we will apply it into nonlinear single degree of freedom system and apply dynamic analysis. Then from that we will extract the target displacement until the target displacement, because the target displacement we have seen in the first part how to get from two different methods. However, by the assumption of S, modal expansion of forces, the MPA, okay, the MPA will give us only the peak response of the structure for that particular mode. So because pushover analysis is static analysis procedure, so pushover analysis is static analysis, we get only the peak. It is like nonlinear time history analysis. It is not like UMRHA, because UMRHA we will find for each mode separately and we will see. But here in the MPA we will get only the maximum. It will not give us the fluctuating response of the structure as we get from UMRHA, but MPA is more practical than UMRHA procedure. So nobody perform UMRHA, mostly people are using MPA, modal pushover analysis. So the only difference, now it is clear, the forces we apply, the modes we apply is progressively. That is only difference. Just like UMRHA analysis, let us see the elastic and inelastic system separately. For linear system, the modal pushover analysis is based on the idea that we can apply the effective earthquake force for any nth mode separately to each structure, and we don't apply it just once but in progressive. But in UMRHA we apply it once or cyclically, and we get the pushover curve, what we have seen all the procedure. But the only difference here is this is static analysis and the forces are applied progressively with different steps, and for each steps we will extract the responses and we find only the peak responses, not the fluctuating, because we will not find the like UMRHA, it can give us the fluctuating as well. Okay, the modal pushover MPA, linear elastic system. So this is the same as response spectrum procedure. The response spectrum analysis procedure, which is a dynamic analysis procedure, can be interpreted in two ways: as static analysis or as pushover analysis. Because the same we are using static analysis of the building subject to lateral force Fn, Sn times An. This is equal to modal participation factor mass matrix times Vn times An, will provide the same value of Rn. This is for that particular mode. The peak value of nth mode response, Rnt, yeah, as obtained from the response spectrum procedure, where An is equal to a function of t and xi, the pseudo acceleration spectrum ordinate corresponding to the natural vibration period Tn, and damping ratio of the n of the nth mode. So A is the pseudo acceleration. There is nothing. Just you have pseudo acceleration, you have phi, you have m, you have modal participation factor, so you can find f. This is response spectrum analysis, the same as response spectrum analysis. Alternatively, this peak modal response can be obtained by linear static analysis of the structure subjected to monolithically increasing lateral force. Instead of applying was monolithically increasing lateral force with an invariant height-wise distribution of Sn. This is the point, m times phi n, pushing the structure up to the roof displacement of URN, because we have target displacement. This is the idea. URN is the peak value of the roof displacement due to the nth mode and given by this formula. URN is mass participation factor, phi, modal, shape, and dn. So for that mode, so dn is again is the ordinate of the deformation response spectrum corresponding to the period of Tn and damping ratio of the nth mode. So you can find it from displacement response spectrum with the time period of your structure. You can find it, and this mode shape and mode participation factor for each mode, for each floor, multiply it, and you can find your peak for your structure. Inelastic system, the peak response Rn of the inelastic system, P effective for that mode only, is also determined by a pushover analysis, which is now a non-linear static analysis instead of linear static analysis, because our structure is non-linear, of the structure subjected to lateral force distribution over the building height according to Sn, with the force increased to push the structure up to the roof displacement URN. So URN is, this is for that mode only, for nth mode. dn is, we found it from response spectrum. Once we know the time period of our structure, is now peak deformation of the nth mode in elastic single degree of freedom system instead of the nth mode elastic single degree of freedom system. So we changed it into non-linear. So this is a governing equation. At URN, the result of non-linear static analysis provide an estimate of the peak value Rn of the response quantity Rnt for displacement, story, drift, and other deformation quantities. Again, nonlinear static analysis using force distribution, this is the underlying idea, leads to the nth mode pushover curve, a plot of base shear versus roof displacement. We talk about this million times. From the nth mode pushover curve is obtained the force deformation curve for the nth mode inelastic single degree of freedom system, which is required to determine dn from the following equation. So we discussed it already, this one. We will find Fsn, Ln, and dn from the curve, because we apply the force deformation curve, the pushover curve, and we idealize it into Fsl dn curve. Then we assign it to nonlinear single degree of freedom system. Then we perform the linear dynamic analysis, and we find single degree of freedom system. We can find Fsm over L and dn from that analysis, and we will change it into multiple degree of freedom system. So if you need, this is the force and displacement in the two sets of curves are related as this one. This is how we change dn is equal to urn like this, and Fsn Ln is equal to this one. So dn and this one change it from the force deformation curve, from a pushover curve, and we can find it where mn is equal to Ln times modal participation factor is the effective modal mass. Now sorry. So this is how we change. This is our force deformation. So we have idealized curve, we change it into this curve. So if we assign the force deformation curve to our nonlinear degree of freedom system and apply earthquake and find the response of the structure, then we are performing UMRHA, that's all. But what we are going to do, however, if you assume the peak, for example, this is our curve. If we assume the peak value from FD curve, from our force deformation curve, and extract the result at that level, just like single mode pushover system, then we can simply say it is modal pushover analysis. This is the underlying idea. If we apply this into single degree of freedom system, and if we perform, if you apply the ground motion and extract, that is UMRHA. But the point here is, instead of performing dynamic analysis, we approximate the target displacement in the curve, and we assume that the maximum, not assume, we have 2 meters. Using that 2 meters, we will find target displacements, and if we extract the responses for that target displacement, then we are performing modal pushover analysis. So this is what we have S here. So the modal pushover analysis, what we are going to do, we have S here. So we have first mode, then we apply this first mode progressively, then we will get this target displacement, then we will go to our pushover curve and extract the response. Again for the second, again third mode, that's all. Then SRSS or CQC the result. Then if we are doing like this, then this is modal pushover analysis. Modal pushover analysis. Nonlinear response history analysis, directly apply UG dot and apply for we discussed it already. But if you apply the modes, this is PTM, this is the special distribution. We have special distribution and we have to use it for each mode, mode 1, mode 2, mode 3. Then for total effective force, we have contribution from each modes, and for each mode apply, instead of once like UMRHs, you simply apply progressively, and after application progressively find the maximum phi displacement and go to your pushover curve and extract the any result, moment, shear, rotation or whatever, and SRS is the result. Then we will done. The whole procedure in a nutshell. Actually we want to calculate the peak in elastic demand subjected of structural nonlinear under an earthquake. So what we know, our special distribution of effective earthquake force S, we decomposed the special distribution S into modal contribution of special distribution. Now for each special distribution modal inertial load pattern, we carry out pushover analysis. Like this is the first mode, will give us the first load pattern. M-phi2 will give us second load pattern. M-phi3 will give us the third load pattern. Then we will construct pushover curve separately for each mode. Then for each pushover curve, we have to estimate the target displacement separately using any of the methods we use to determine the target displacement. After we get the target displacement, then we go to the pushover analysis of that mode and extract all the responses of that roof displacement, which is equal to the target displacement. Then all the responses will be combined with SRSS or CQC method to get overall response of the structure. This is what we did. So for each special distribution, we will do pushover analysis. Then it will give us 3 load patterns. Then we will construct pushover curve separately for each mode according to the pushover. Then but this one will come at the end. We can say that NPA is nonlinear version of response spectrum analysis. This is the nonlinear version of response spectrum. But the response spectrum analysis, we apply the effective earthquake force once to the elastic system. But here in the NPA, we apply the effective earthquake forces for each mode separately and in a pushover manner, and extract the response separately for each mode, and we will use SRSS or sequestry to get the overall response. That is the only difference. So in RSA we apply once and we extract the modes, and we have a lot of formulas. You can check the video in my other video for response spectrum analysis. We make also Excel sheet how to calculate response spectrum. But in MEP it's a pushover analysis. We don't apply the force once, but we have to perform it progressively. That is the only difference. So UMRHA with MPA now. The response value Rn determined by pushover analysis is an ultimate or peak value of the response of the inelastic structure to that ends, but is not identical to another estimate determined by UMRHA. So the peak, because this one have applied the force once, and we will extract the response for each nonlinear degree single degree of freedom system. But for MPA it will give us only the peak. For elastic analysis, UMRHA is equal to modal response history analysis. It is the same for elastic analysis, and MPA is the same as response spectrum analysis. There is no change for elastic. But for inelastic system, the two UMRHA and MPA estimates of the peak modal response are both approximate and different from each other. The only exception is the roof displacement, because it is deliberately matched in the two systems, because when we perform we have to. For inelastic system, the two procedures are approximate systems, and they will give different results because the underlying idea are different. MPA is based on the pushover analysis idea. UMRHA is based on the uncoupling of modal shape and solving for each mode separately with the use of a spatial distribution concept. The same equation of motion, but for nonlinear system like classical model. So both of the response will be different, except the roof displacement, because it is deliberately matched in the two. Okay. So UMRHA and MPA procedure, the two estimates differ because the underlying idea is different, and again the UMRHA is based on the approximation as we saw it, contributed to the ends mode displacement as approximate, which is avoided in MPA because the floor displacement, story drift and other quantities are determined by nonlinear static analysis using force distribution, not that one. SN. As a result, the floor displacement of the inelastic system are no longer proportional to the ends mode shape. No longer proportional to the ends mode shape, because most of the time the mode shape is the same as the force, but here forcefully we are applying it, so in elastic system no longer proportional to the ends mode. It contrasts to this one. In this sense, the MPA procedure represents the nonlinear behavior of the structure better than UMRHA. However, the MPA procedure contains a different source of approximation which does not exist in UMRHA. The peak modal response RL for each contribution each determined by one nonlinear static analysis, are combined by a modal combination, just like in RSA of linear system. This application of modal combination rule to inelastic system lacks a rigorous theoretical basis, but seems reasonable because the modals are only weakly coupled. This one is also, we saw it in the UMRHA. Once you get the response for each mode in a time domain, you simply sum directly to get the overall response of the structure. But in MPA, once we get the peak response, we have to SRSS or CQC to determine the overall response of the structure. Okay, that is all about the two pushover. This is practical approach for nonlinear modeling. We have nonlinear modeling. I will show you the results, but just to show you nonlinear modeling, we have in the material level or cross-sectional level or member level. So cross-section and member level, we have plastic hinge modeling approach, and nonlinear model, we have fiber hinge approach. Plastic hinge modeling, cross-section level, defining inelastic behavior, and member level. So we have different hinges: moment curvature, shear hinge, axial hinge, torsion hinge. The same is true for member level. So whichever nonlinearity you want to capture, you have to assign. Plastic hinge approach, flexural hinge, we have two types: moment curvature and moment rotation. This is for member level, this is cross-section level. So flowchart. Finally, I want to show flowchart aid for selecting appropriate nonlinear, elastic, and component model. So this is how we are going. This is a good flowchart. I get it from the slide. So you have element model. So you have element modeling. So you need detail modeling or not? If it is yes, you have to use continuum modeling. If it is no, then use discrete methods. Okay. So after you choose this one, again you have to choose force or deformation controlled. Which one you need? If it is force controlled, so all the force deformation curves, everything will be given in the force, and the IO, CP, everything labels will be in the force. So if it is force, then modeled. It is modeled, yes. If it is no, then here. If it is modeled, then modeling using linear elements. If it is no, check as non-simulated failure mode. Then if we choose deformation, if you choose deformation method, then concentrated or fiber section. So you will choose. If it is fiber, you have to use fiber section modeling. If it is concentrated, you have to use concentrated hinge modeling. If it is fiber section modeling, then you come here and again you have to choose. This one, hanging expected at element in only or not. If it is yes, you have to go to lumped plastic element. If it is no, distributed plastic element. Again, once you choose this, add in the spring for representing other behaviors, something like that. If you choose concentrated, then you have to use concentrated hinge modeling. Then you have to know degradation, important because hysteresis loop. Then if it is no, use type C model, figure 2.6, you can see that. Then if it is yes, then cyclic degradation is important. If it is no, again here, then if it is yes, use typical model. In this way you can check. So I really highly recommend. If you are interested, you can see modeling for structural analysis by Grams Paul. This is his book, Dr. Grams H. Paul. So modeling for structural, you can see for detail. In addition to that, you can see also this is the full nonlinear detailing approach, step by step. It has presentation, and everything is included here with Professor Fouad also. So you can see concentrated modeling, this distributed and concentrated hinge approach. What does it mean? This fiber hinge approach, continuum, everything explain it. So just to wrap up very quickly, I will show you ASC 41 approach for nonlinear modeling of structural component. They have a lot of procedures, guidelines and everything. ASC 41 prescribes nonlinear modeling parameter and acceptance criteria for various structural components, because to find force deformation is not easy. So for each force deformation curve, this guideline ASC 41 has a table. So for modeling parameter and acceptance criteria, once we find that, even in ETABS I will show you, it has capability for automatic assignment, but it has its own shortcoming also, because when we assign automatically the force deformation and hysteresis, for the hysteresis assignment part for automatic, it will not give you an option to choose which type of hysteresis curve you use. So that is the only problem for the beam, for the column, everything. MP, this modeling parameter used to build analytical model of structure for seismic evaluation and acceptance criteria, everything. So as per ASC 1417, generalized F up to D realization A, B, C, D, E. As you can see, we have A, B, C values. So IO level, LS level, CP level, acceptance criteria, immediate occupancy, life safety, collapse prevention. This is the source where we have find. This is first the material ductility start here. So one means the capacity reached, so Q over QY is equal here, so that's why it's 1. Again, there is a lot of representation. This is for deformation, this is for deformation ratio. You can add also so this is trilinear response deformation ratio. This is all is found in ASC 4117. You can check it. So this is perform 3D instead of A, B, C, D points. They have YUL RX system, so you can define everything you want, URLX system or no strength loss or strength loss. This is optional, full strength loss deformation, everything is here. And hinge property also, this is 5 A, B, C, D. Then we have IO, LS, CP level, the acceptance criteria marked on the deformed shape. So this is what we are going to give, what we give in our nonlinear system. What is point A, point B, point C? It's everything is given. Please read it, because point A is always the origin. Point B represent yielding. No deformation occur in this hinge up to point B. So this is the point of yielding regardless of the value specified for B. At point B will subtract from the point C represent the ultimate capacity for pushover analysis. This is point C is the ultimate capacity. Point D represent the residual strength of pushover analysis. This point D is residual, and point E is already fair. They represent total fair. Behind E, the hinge will drop load down to point F. No shown, but it will drop down F. So it will go like that. So in ASC 4117 modeling parameter and acceptance criteria for RC beam, this is a ABC. This one, as we have, this is A, B, C, this one A, B, C. If you get A, B, C, then you can construct. So this is A, B, C, and IO, LS, CP level. IO, LS, CP level is given, and this is a procedure. You have to see, for example, let me make it. So condition, for example, for your beam, first this reinforcement balanced this alpha minus this is a formula then you have to use for upper reinforcement and down reinforcement balanced and this and transverse reinforcement. C, what is C is here C and end C, confirming and non-confirming, what is non-confirming and what is confirming. You have to see here, everything is written here. So down you can see, then this formula, then once you know confirming non-confirming, like this beam controlled by fracture, this is controlled by shear, this is controlled by development of space along space, this is column joint, something like that. So again you can see here, this is for the beam, this is for the beam, balanced failure, this is still a ratio. So you can read it, the design longitudinal reinforcement top and bottom, as I showed you. This is for the top, this is for the bottom, this is for the balanced. So confirming, non-confirming, and everything, tensile reinforcement ratio, phi, compressive reinforcement ratio, balanced, everything expected, because the expected concrete strength is 30% higher than the normal, the nominal strengths. So in ETABS directly you have these tables, all these tables are in ETABS. Once you choose, you can find it. Then if you choose from the table, you will directly use it. You see ASC 4117, directly you choose from there. Concrete beam, M3 is the type of freedom, dead load or light load, from where V comes from. There is a lot of calculation how to find this V, because this V shear force is the maximum shear force in the maximum moment after you apply your loading in your nonlinear structure. So this V should be determined. This is drop load after P point E or extrapolate. So just to know what is 0.1, 0.2, again I found this from the sources here and from Dr. Professor Fuad Najim. Rotation 0.01 means this is a beam, and in the experiment there is no crack, there is nothing. But rotation 0.02 means there is some crack. Rotation 0.05 means like this, 0.06 means like this. So when you read this, you can understand what is 0.05, 0.04, 0.02 means. You can visualize here. So this is for the colon also. The colon, they have directly formula A, B, C, they have direct formula. Please read it. And this footnote also here, what to do. But ETABS has directly can give us. This is RC beam joint. The footnotes are here, please read it. Two-way slab also, this is very important. Okay, so thank you so much. Let's go to, this is our presentation. Let's go to here. Let me show you some things very quickly. So for us, this is a 44-story building. This is nonlinear. So as per our discussion, I hope you get something from our discussion. So let me remove this nonlinear. Let me remove it. So after we perform define, let me show you the load pattern. This is the load pattern we have. Define load cases. In the load cases, we have pushover. So we have pushover X and pushover Y. We have nonlinear modeling. Then if I show you modify showcase, this is pushover. So nonlinear static, mass sources, and we have mode shape 1 and mode P delta analysis, and we assign load application at displacement controlled, and our is 2% of our building, and the mode story 44, and this is the node 20, joint 20, that's where we applied. and floor crack, and this result save nonlinear parameters, everything you can go and see. This is nonlinear parameter, iteration, solution, maximum step, we have to use maximum null steps, maximum stiff iterations. These are very important, but you can use the default also. Crack analysis, again results saved. This is also multi steps like that. So this is also, we change it, dead load, we change it into nonlinear also, because we have to start from this nonlinear, because we change, I will show you here, this nonlinear static, we change the load into nonlinear static. So the same is true in the y direction. This is what we apply, p delta analysis from modal, and everything is applied. So the analysis was done and it's already logged. So if you want to see for example y, if you want to see these points, for example IOLC, so we apply already force deformation curves for each point. For beam and collant we use plastic hinge modeling. For shear wall we use shear we used fiber hinge modeling. So wait, let me make it center, if you can see it better. There is, okay, let's go for example how many steps you see, the pushover steps which are pushed until 46. So let's go and see the final push. This is sometimes happens. Okay. Okay. In the x direction we have 9. Sometimes it happens like this. Okay, I want to just show you the for example okay, let me open which one I open. I have a lot of, wait, let's try once. For example okay, now it comes. Okay, let me show the final one. 46. Otherwise we will check others. Okay. Let me check 5 for example, because once okay, it has problem. Let's open it again. Okay, before that let me show you another result. For example display, then you can see story responses. story responses, then you will choose, for example, push X. For push X, you can see step number 1. This is step number 1, output type, and this is step number 1. Then for example, step number maximum or minimum, you can choose maximum, and this is the maximum. As you can see, 44 story, and the steps around 46 steps. You can see maximum story displacement, maximum story drift, it's extracting, but it will take time. I will show you the pictures also. This is story displacement. Okay, this takes time. I don't wanna wait. I will show you the result. 400 story and 44 story we did. I want to show you. It is for my computer. It is heavy. It will take much time to take. Stuck. I apologize for the inconvenience. Okay, it comes. Okay. So okay, that was the discussion and all the results, global responses and local responses, moment, shear, everything you can extract like that from the let me close it. Yeah, this one. And okay, so okay, thank you. So I have a video or a photo I can show you, because this one will take much time. Because nonlinear modeling is heavy, that's why this is also part of because we have to use Perform 3D, because it is very powerful software, but it performs, but it needs it's not that much powerful. Let me close some programs. To change it here. Okay, 44 story. Output result, video. We have video, but we have picture also. Let me show you picture, because these are some of the pictures. Anyways, this is in a nutshell, this is the pushover analysis, and the same thing is true. Just to finalize, nonlinear time history analysis also performed, and the ground motion, everything is the same, and the building type is also 100 story and 44 story was done. So the response also was also taken from nonlinear time history analysis also in the. So this video will finalize our demonstration. So we finished classical model analysis, linear time history analysis, response spectrum analysis, and pushover analysis, and nonlinear time history analysis is performed, and the results will compare, and at the end of the day, with some modification, we will try to publish this paper as per the help of my advisor, Dr. Anna and Professor Vivian. I really appreciate for this long video. I didn't expect like this, but it went far. So this is also, I sent this presentation also, so you can check it. Just let me go through once. This is the type of analysis, this is the activity, this is we already discussed already. This is a pushover curves. So concrete Menders, I wanted to show you something, but it is very long. So this is Menders unconfined and confined strengths, but I'll show you later. This is for hinge lengths also. So this is all the tables I showed you already. It's very important to see. This is the methods we use. So this is the result. This is the result, and the result is like this, because I couldn't show you now, but the result will be shown like this. It will show you which hinge pass which area should be shown like this. Okay, this is what I wanted to show you, but I couldn't show you, but this is a result. At the end of the day, we have to find like this. This is also the same. This all the results should be extracted like this. It will show you like this, and the energy dissipation also, and this one also, how with respect to one target IO level, the others also checked like this. And the pushover curve, this is the displacement and pushover curves. This is also drift. This is, as I showed you, nonlinear. This is a pushover curve, base shear with displacement. This is a performance. It will show you the capacity and demand. So the capacity is green and the demand is in red. As you can see, capacity and the bilinear idealized is here. So we have the capacity and the demand is here. We can see like that. So we can see a lot of different 400 story also, 400 story also, the pushover curves, the demands, everything was captured. And this is how the plastic hinge formation also captured. I wanted to show you live, but it will take much time. I couldn't show you like this. So the same thing is true for nonlinear time history analysis also. The ground motion is the same. This everything was discussed. Everything we discussed already in the. This is the method we use for nonlinear direct integration. This is central differential method, Newmark's method, concentrated averages, acceleration, linear acceleration method, Winsell data method, nonlinear system, central, all was discussed. So the selection and modification of ground motion was discussed, how to get, everything was discussed. This Jaipur distance, what is the rupture distance, and everything what we feel here, this all discussed, and scaling also discussed, and the result for nonlinear, and this is for Ethiopian code, and the result and findings for will be discussed. So in a nutshell, that is the discussion. So I really appreciate for your time this long, Dr. Anna and Professor Vivian. I would like to thank you.